The first thing the camera learns in a shallow reef is that stillness is not safety. Sunlight pours down in fractured beams, bent by the surface and scattered by suspended sand, and everything looks calm in the way only danger ever does. The seabed appears empty at first glance, a patchwork of pale sand, broken coral, algae-coated rock, and the quiet debris of a reef constantly grinding itself into dust. Nothing moves except the lazy drift of particles in the water column and the distant flicker of small fish, keeping a respectful distance from the bottom. It is here, in this visually unremarkable space, that the stonefish completes its illusion. It does not hide by absence, but by excess. Its body does not vanish into the environment. It overwhelms the eye with texture. Lumps mimic eroded rock. Skin folds resemble algae. Mottled browns and greys copy the mineral palette of reef rubble so precisely that even a trained observer must pause and recalibrate their vision to separate animal from ground. The stonefish is not camouflaged like a tiger behind grass or a shark beneath glare. It is camouflaged like a mistake in perception, a flaw in how the brain categorizes shape and threat. Seen from above, the stonefish's outline dissolves into irregularity. There is no clean silhouette, no obvious head or tail, no symmetry to trigger alarm. This is deliberate. Predators rely on recognizing patterns, and the stonefish removes itself from the vocabulary of prey and threat alike. Its dorsal spines, thick and rigid, rise from the back like jagged shards of reef, each one coated in tissue that blends seamlessly with the surrounding rock. These spines are the only part of the animal that breaks the horizontal plane of the seabed, and even they do not advertise danger. They look passive, structural, inert. Only when the camera moves closer does their geometry become unsettling. They are evenly spaced, mechanically precise, and anchored to musculature designed not for swimming, but for resistance. The stonefish does not flee when approached. It does not need to. Movement would ruin the illusion. Survival here is achieved by refusing to react at all. Camouflage is the stonefish's first weapon, and it is not merely visual. Its skin supports colonies of algae and microorganisms, further softening the boundary between animal and substrate. This biological cooperation enhances the disguise over time, turning the stonefish into a living extension of the reef. Even scent plays a role. By remaining motionless and embedded in the chemical background of the seabed, the stonefish avoids producing the metabolic signals that many predators use to detect prey. In evolutionary terms, it has opted out of the chase entirely. This is not an ambush predator in the conventional sense. It does not stalk, lunge, or pursue. It waits for the environment itself to deliver opportunities, and it waits without urgency. Energy conservation is part of the strategy. In warm, shallow water, where oxygen fluctuates and temperatures rise, unnecessary movement carries metabolic costs. The stonefish spends most of its life conserving energy, lowering its baseline demands, and relying on camouflage to do the work muscles usually perform. When prey arrives, the interaction is brief and violent, but even this happens with minimal motion. Small fish, crustaceans, and invertebrates drift too close, mistaking the stonefish for a harmless rock or a patch of reef. The stonefish does not chase them. Instead, it opens its mouth with startling speed, creating a sudden drop in pressure that pulls water and prey inward. The suction feeding mechanism is efficient and silent, requiring only a fraction of a second and leaving almost no disturbance behind. The seabed returns to stillness immediately afterward, as if nothing has happened. There is no pursuit, no visible struggle, and no warning to nearby animals. This is predation without spectacle, a reminder that most successful hunters are invisible. Yet it is not the stonefish's hunting method that has made it infamous. It is the second weapon, reserved not for prey, but for anything that makes contact. The dorsal spines that appear so inert are, in fact, part of one of the most sophisticated defensive venom systems in the ocean. Each spine is connected to a venom gland at its base, and the system operates mechanically rather than actively. The stonefish does not inject venom by choice. It does not strike or stab. The delivery system is pressure activated. When weight is applied from above, the spines are forced downward, compressing the venom glands and driving venom through grooves along the spine and directly into the puncture wound. The stonefish does not need to react. The act of being stepped on completes the mechanism automatically. This design is crucial to understanding why the stonefish is so dangerous in shallow reefs. Unlike venomous snakes or aggressive predators, the stonefish does not initiate conflict. There is no attack sequence to observe or avoid. The danger exists passively, embedded in the environment itself. Shallow reefs are zones of overlap between humans, large animals, and the seafloor. They are places where people wade, where fishermen step off boats, where turtles graze, where rays bury themselves, and where visibility is often compromised by glare, turbidity, or wave action. In these environments, eyes are focused forward, not down. Feet land where they can, not where they should. The stonefish exploits this behavioral gap perfectly. It occupies the exact space where attention is weakest. The venom itself is a complex cocktail of proteins designed to cause immediate and overwhelming physiological disruption. Upon injection, it spreads rapidly through surrounding tissue, triggering intense pain, swelling, and vascular effects that can incapacitate even large animals. The pain is not incidental. It is the primary function. In evolutionary terms, venom is not meant to kill intruders outright, but to create such a strong negative reinforcement that contact is never repeated. For predators, this means release and retreat. For large animals, it means immobilization and vulnerability. For humans, it means a medical emergency that escalates within minutes. The venom's effects are amplified in shallow, warm water, where circulation is already elevated and absorption is rapid. The stonefish's defense is calibrated for this environment, where escape routes are limited and reaction time is short. From an ecological perspective, this venom serves a broader role than individual defense. By occupying shallow reef flats and rubble zones, stonefish influence how other animals move through the environment. Grazers avoid certain areas. Predators learn caution. The seabed becomes a patchwork of risk zones, shaping traffic patterns and feeding behavior across the reef. In this way, the stonefish functions as a static regulator of space. It does not chase competitors away, but its presence alone alters how the ecosystem is navigated. This is an underappreciated form of ecological control, one that relies not on dominance or aggression, but on consequence. The irony is that the stonefish's greatest weapon is entirely dependent on being ignored. If it were noticed consistently, it would lose its advantage. Its survival depends on the assumption that eyes and minds will misclassify it as part of the environment. This makes shallow reefs uniquely dangerous, not because they are teeming with active threats, but because they are filled with passive ones. The stonefish thrives in these transitional zones, where land meets sea and perception fails most often. It is not found in deep, open water, where attention is constant and movement is required. It belongs to the margins, the places where vigilance relaxes. As the camera lingers, the illusion begins to fracture. Subtle movements become visible. A slight expansion of the gill covers. A faint shift in the sand as the fish adjusts its posture. The spines, once dismissed as rock, now appear too regular, too deliberate. Recognition arrives late, and that delay is the point. The stonefish does not announce itself because it does not need to. It does not warn because warning would require cooperation from its victim. Evolution has selected a simpler solution. The stonefish does not attack. It waits. And when contact is made, the environment itself delivers the punishment. In this ecosystem, survival is not always about speed, strength, or intelligence. Sometimes it is about becoming so convincingly inert that the world forgets you are alive at all. The stonefish has perfected this strategy to its extreme conclusion. It wins without moving, not by chasing threats away, but by ensuring that any creature careless enough to touch it will remember the encounter forever. You do not get attacked here. You get punished for contact. The reef at mid-depth looks calm in the way only structured chaos can. Coral heads rise like frozen explosions, each surface alive with algae, sponges, and the constant motion of grazing fish. Light filters down in shifting bands, breaking apart as it strikes uneven stone and living architecture. Every crevice is occupied, every overhang contested, every open corridor watched. This is not empty space. It is a crowded, three-dimensional maze where survival depends on reading geometry correctly. Movement here is cautious and directional. Small fish hug edges, darting between shadows, always aware that the shortest path is rarely the safest one. In this environment, the lionfish does not appear at first as a predator. It appears as decoration. Its elongated fins trail outward in delicate arcs, striped in reds, whites, and browns that echo the colors of branching coral and feathered invertebrates. It hovers with minimal effort, pectoral fins fanned wide, body nearly motionless, as if suspended rather than swimming. Nothing about it suggests speed or aggression. That misjudgment is where the trap begins. The lionfish is not built for pursuit. Its body is laterally compressed, optimized for hovering and precise control rather than bursts of acceleration. Its musculature favors stability over power, and its swimming style reflects this constraint. Instead of rapid tail beats, it uses subtle fin movements to maintain position in complex currents. This is not a limitation to be overcome. It is a design choice. In dense reef structures, chasing prey is inefficient and often impossible. Corridors are narrow, visibility is fragmented, and prey know the terrain better than most hunters. The lionfish has solved this problem not by becoming faster, but by turning the environment itself into a weapon. Its fins are not for propulsion alone. They are tools for spatial manipulation. As the camera drifts closer, the fins come into focus as more than ornamental extensions. The pectoral fins extend outward in a wide semicircle, forming a soft but imposing perimeter around the fish. Each fin ray is stiffened, controlled independently, and capable of subtle adjustments that alter the shape of the lionfish's silhouette. To prey, this creates a visual paradox. The lionfish appears large, complex, and difficult to interpret. The fins break up its outline, making it difficult for small fish to judge distance, orientation, or intent. In reef environments where split-second decisions determine survival, confusion is as dangerous as speed. The lionfish exploits this cognitive weakness relentlessly. Venom plays a critical role here, but not in the way many predators use toxins. The lionfish's venom is defensive, housed in grooves along its dorsal, anal, and pelvic spines. These spines are rigid, sharp, and positioned to discourage contact from above or behind. The venom is delivered passively when pressure is applied, much like the stonefish, but its purpose is deterrence rather than immobilization. Predators that attempt to bite or swallow a lionfish are met with pain and inflammation that reinforce avoidance behavior. Over time, this allows the lionfish to operate in open view without being harassed. It does not need to flee or hide. Its venom grants it psychological territory. Other fish learn quickly that the cost of contact is not worth the risk, and this learned avoidance creates a buffer zone around the lionfish, an invisible clearance that it uses to its advantage. Within this buffer, the lionfish begins to hunt. The process is slow and deliberate. It positions itself near vertical surfaces, coral walls, or overhangs where escape routes are already limited. Small fish approach, drawn by curiosity or mistaken safety, and the lionfish subtly adjusts its fins. The pectoral fins extend further, forming a curved barrier that does not block movement entirely, but narrows it. The prey senses an obstruction, but not an immediate threat. Instinct pushes it to flee along the most open path, which the lionfish carefully leaves available. This is the critical deception. The fins do not close in from all sides. They guide. Prey fish rely on rapid directional changes to escape predators, darting sideways into crevices or bursting upward into open water. The lionfish's fin wall disrupts these reflexes. The wide fins block lateral escape, while the coral or rock behind the prey blocks retreat. The only remaining path is forward, directly toward the lionfish's head. This is not coincidence. The lionfish aligns itself so that the perceived exit leads straight into its strike zone. To the prey, the fins appear as soft obstacles, less threatening than the solid reef behind or the open water beyond. The prey chooses the wrong escape path because it is the only one that seems available. This funneling behavior is one of the lionfish's most effective adaptations, and it reveals a deeper principle of predator-prey interaction. The lionfish does not need to overpower its prey physically. It needs only to influence decision-making under stress. By controlling space rather than speed, it forces prey to participate in their own capture. When the moment comes, the strike is sudden and efficient. The lionfish opens its mouth rapidly, creating a powerful suction that draws water and prey inward. The jaws expand far beyond what its body size would suggest, and the prey disappears almost instantly. There is no chase, no prolonged struggle, and minimal disturbance to the surrounding reef. The trap resets immediately. This method is especially devastating in ecosystems where prey species have not evolved alongside lionfish. In regions where lionfish are native, prey have learned to recognize the fin display as a threat and adjust their behavior accordingly. They keep greater distance, respond earlier, and avoid the funnel entirely. In invaded reefs, however, this recognition is absent. Prey approach too closely, misinterpret the fins as shelter or harmless structure, and react too late. The result is unchecked predation that reshapes reef communities rapidly. Juvenile fish populations decline, grazing pressure shifts, and algae begins to overgrow coral as herbivorous fish are removed. The lionfish's hunting strategy does not just capture individual prey. It alters the balance of entire ecosystems. The irony is that this impact is achieved without aggression or speed. The lionfish is a patient manipulator, relying on the predictability of fear responses. Under threat, prey do not behave randomly. They follow evolved rules that have worked against most predators for millions of years. The lionfish has found a way to exploit those rules by presenting itself not as a pursuing threat, but as an environmental constraint. To the prey, it feels less like being hunted and more like making a series of increasingly bad choices in a shrinking space. From a physiological perspective, this strategy is remarkably energy efficient. The lionfish expends minimal effort during the hunt, conserving calories in nutrient-poor environments or during periods of low prey availability. Its slow metabolism and precise fin control allow it to remain effective even when food is scarce. This efficiency contributes to its success in new environments, where it can survive and reproduce rapidly without the energetic demands faced by more active predators. The venom further supports this lifestyle by reducing harassment and allowing the lionfish to hunt openly without expending energy on defense. As the camera pulls back, the scene repeats itself with subtle variations. Another prey fish enters the perimeter. The fins flare slightly wider. The coral wall becomes a dead end. The open water narrows. The prey hesitates, turns, and commits to the wrong direction. The strike follows. The reef barely notices. This is not spectacle hunting. It is quiet restructuring, one decision at a time, one funnel at a time. The lionfish's success challenges common assumptions about what makes a predator effective. It is not strength alone, nor speed, nor even venom in isolation. It is the ability to shape the environment in ways that prey cannot perceive until it is too late. By turning its own body into a living fence, the lionfish converts open reef into a controlled corridor. It does not chase. It does not rush. It waits for prey to move themselves into the trap. In a world where survival often depends on choosing the right path in a moment of panic, the lionfish wins by ensuring that every visible escape leads exactly where it wants. The reef narrows where light begins to fracture. What was once an open garden of coral heads and sand channels compresses into a lattice of cracks, ledges, and undercut walls where water slows and shadows thicken. This is not empty space. It is a maze carved by erosion and growth, a three-dimensional grid where bodies must bend, flatten, and slide to pass through. Here, speed loses its meaning. There is no room to sprint, no clear line of escape, no distance to build momentum. Movement becomes intimate and constrained, dictated by geometry rather than muscle. It is in these tight corridors that the sea snake appears, not with the drama of a charging predator, but with the quiet certainty of something perfectly designed for this environment. The body arrives first, a long, laterally compressed ribbon gliding through the water with almost no visible effort. The tail is flattened like a paddle, gently sculling side to side, while the rest of the body flows forward in smooth, controlled waves. The head is small and narrow, barely wider than the neck, allowing it to slip into spaces where bulkier predators simply cannot go. Scales catch the light briefly, patterned in bands or muted tones that dissolve into the reef's visual noise. There is no rush. Sea snakes do not advertise urgency. Their hunting strategy depends on patience and proximity, not pursuit. Unlike many marine predators, sea snakes are air breathers, returning to the surface periodically to replenish oxygen. This constraint has shaped their physiology in subtle but powerful ways. Their lungs extend through much of their body length, functioning not only for respiration, but also as buoyancy control. By adjusting air distribution within this elongated lung, the snake fine-tunes its position in the water column, allowing it to hover, sink, or rise with minimal movement. This ability is crucial in reef cracks, where sudden fin strokes or tail flicks would betray presence. The snake does not fight the water. It becomes part of its slow, deliberate flow. The prey here is small, fast, and accustomed to danger. Reef fish that live among cracks and crevices survive by reacting instantly to threats, darting deeper into the maze, or exploding into open water if space allows. These reflexes are effective against most predators, which rely on surprise followed by speed. But in this environment, those rules fail. A fish tucked into a coral fissure cannot accelerate. It can only pivot, reverse, or press itself tighter against stone. The sea snake understands this implicitly. It does not strike in open water where prey can flee. It hunts where escape collapses. As the snake advances, it probes with its head, tongue flicking to sample chemical cues suspended in the water. This sensory system, refined over millions of years, allows the snake to detect prey without sight alone. In the low light and visual clutter of the reef interior, chemical information often arrives before shape or movement. The snake reads these signals carefully, aligning its body with cracks that carry the strongest traces. Each turn is measured. Each pause is intentional. The hunt unfolds slowly, almost invisibly, until the distance between predator and prey shrinks to a matter of centimeters. The strike, when it comes, is brief and economical. The sea snake does not coil or lunge dramatically. In tight spaces, such movements would be impossible. Instead, it delivers a quick, precise bite, jaws snapping shut around the prey for only a fraction of a second before releasing. There is no attempt to hold, wrestle, or swallow immediately. The snake withdraws almost instantly, reversing its body through the crack with practiced ease. To an observer unfamiliar with sea snake behavior, this might look like hesitation or failure. In reality, the decisive moment has already passed. The venom does the rest. Sea snake venom is among the most potent in the marine world, but its power is often misunderstood. It is not designed to cause explosive damage or dramatic external symptoms. Instead, it targets the nervous system and muscles with ruthless efficiency. The toxins interfere with neuromuscular transmission, disrupting the signals that allow muscles to contract. The result is a gradual but unstoppable shutdown. Muscles weaken. Coordination falters. Breathing becomes difficult. The prey does not thrash violently or flee in panic. It simply loses the ability to function. In the confined geometry of reef cracks, this effect is amplified. A fish weakened by venom cannot drift away or hide deeper. It remains trapped in the same limited space, its options narrowing with each passing second. The snake does not need to pursue aggressively. It waits nearby, monitoring chemical cues that reveal the prey's condition. As muscle control deteriorates, the prey's movements become slower and less coordinated, making it easier to locate and retrieve. The second approach is calm and unhurried. The snake follows the same path back, guided by the same sensory trail, and consumes the immobilized prey with minimal resistance. This bite and retreat strategy offers several advantages beyond efficiency. By releasing prey immediately, the snake avoids injury. Reef fish often have spines, sharp fins, or strong jaws that could damage a predator forced into a prolonged struggle in a confined space. The venom allows the snake to outsource the risk to chemistry, letting time do the work instead of force. This is a recurring theme in venomous evolution. Venom is not just about killing. It is about control, reducing uncertainty, and minimizing the cost of each interaction. From an ecological perspective, sea snakes occupy a highly specialized niche. They are not generalist hunters roaming open water. They are precision predators that shape the behavior of reef communities from within. Fish that inhabit cracks and crevices must balance the safety those spaces provide against the risk of encountering a predator that thrives there. This creates a constant tension that influences where fish rest, feed, and reproduce. The presence of sea snakes subtly reorganizes the microgeography of the reef, turning certain shelters into liabilities. Physiologically, the sea snake is built for this role in ways that go beyond venom and body shape. Many species possess cutaneous respiration, absorbing a portion of their oxygen directly through the skin. This adaptation allows them to extend dive times and remain submerged longer without surfacing, an advantage when hunting in complex reef structures where breaking cover would disrupt the hunt. Combined with efficient oxygen storage and low metabolic rates, this enables the snake to operate patiently, waiting out prey rather than chasing it. There is a quiet irony in how effective this strategy is. The bite itself is often small, barely visible, and sometimes unnoticed by the prey in the initial moment. There is no dramatic wound, no immediate collapse. Yet the internal effects are profound. The prey's body becomes its own enemy as communication between nerves and muscles breaks down. Strength remains, but control disappears. This mismatch creates a slow unraveling that ends inevitably. The reef does not erupt in chaos. It absorbs the event silently. For humans, this same venom carries serious risk, but encounters are rare precisely because sea snakes are not aggressive hunters. They do not defend territory actively or strike without provocation. Their bites are reserved for prey in constrained environments, delivered with accuracy rather than force. Most interactions with humans occur accidentally, when snakes are handled, trapped, or startled. Even then, many bites are dry or low dose, reflecting a venom system optimized for small prey rather than large threats. The danger lies not in hostility, but in the potency of a system designed to end fights before they begin. As the camera follows the snake deeper into the reef, the pattern repeats. Slide, pause, sample, strike, withdraw. Each movement is minimal, each decision refined by evolutionary pressure. There is no wasted energy here, no flourish. The sea snake does not dominate the reef through presence or intimidation. It dominates through inevitability. In spaces where speed fails and escape collapses, chemistry becomes destiny. This hunting method challenges common narratives about predation. It reminds us that victory in nature is not always loud or immediate. Sometimes it arrives quietly, carried invisibly through tissue and synapse, turning motion into stillness from the inside out. The sea snake does not need to overpower its prey physically. It needs only to interrupt the systems that make movement possible. In the tight corridors of the reef, where every centimeter matters, that interruption is enough. The final image is not one of pursuit or struggle, but of absence. A crack that once sheltered a fish is now empty. The snake has moved on, leaving no sign beyond a brief chemical echo that fades with the current. The reef continues its restless motion, unaware that another small transaction has reshaped its balance. Here, effectiveness is measured not by spectacle, but by certainty. A small bite, delivered precisely where escape is impossible, leads to a collapse that unfolds out of sight. Small bite, big collapse. The reef does not announce danger when it arrives in small, rounded form. Among branching corals and drifting sand, the pufferfish moves with an almost careless ease, propelled by quick flicks of its fins that give it a faintly awkward appearance, as though precision were never part of the design brief. It does not look like a survivor. Its body is compact, soft-edged, and poorly streamlined, lacking the sleek silhouette associated with speed or endurance. Its movements are casual, sometimes clumsy, and it often drifts into open water where better defended fish would never linger. In a system governed by constant predation, this behavior appears reckless. Yet the pufferfish persists, not by avoiding attention, but by transforming attention itself into a liability for those who offer it. From a distance, the pufferfish blends into the reef's visual noise through understatement rather than camouflage. Its coloration is often muted, pale browns, yellows, or greens patterned with spots that mirror sand grains or coral polyps. It does not hide aggressively, nor does it seek the tight refuge of cracks and crevices. Instead, it occupies the middle ground, grazing on algae, small invertebrates, and coral growth with a beak-like mouth designed for crushing rather than tearing. This feeding strategy already hints at its true nature. The pufferfish is not built for pursuit or flight. Its body plan prioritizes a different equation entirely, one where survival depends on a single dramatic reversal of power. As the camera follows the pufferfish through open reef water, a larger predator enters the frame. The approach is deliberate, measured, and confident. The predator has seen this shape before, or something like it, and calculates an easy meal. In reef systems, most predation is decided in seconds, often before prey has time to react. The predator closes distance, jaws parting slightly, water compressing ahead of its movement. This is the moment where the pufferfish reveals the logic behind its design. Inflation does not begin as an explosion, but as a rapid intake of water. The pufferfish opens its mouth and gulps, channeling water into an elastic stomach that expands far beyond its resting volume. This process is controlled and mechanical, driven by specialized musculature and connective tissue that allow the body to transform without tearing or losing function. Within moments, the fish's shape shifts from compact and vulnerable to spherical and imposing. The skin stretches outward, and spines that once lay flat against the body rise and lock into place, converting the fish into a rigid, spiked orb that bears no resemblance to prey. This transformation serves multiple purposes simultaneously. First, it dramatically increases apparent size. Many predators rely on quick assessments of whether prey can be swallowed whole. Inflation breaks this calculation instantly. What was once an easy bite now exceeds the predator's gape, turning commitment into a mistake. Second, the spines create a mechanical deterrent. Even predators capable of crushing prey risk internal injury if they attempt to swallow an inflated pufferfish. The spines are not merely decorative, they are reinforced, sharp, and positioned to wedge against jaws, throats, or digestive tracts. Swallowing becomes not just difficult, but dangerous. Yet the most powerful weapon of the pufferfish is invisible. Embedded within its tissues is Tetrodotoxin, one of the most potent natural toxins known in marine ecosystems. This toxin does not originate solely from the fish itself, but from symbiotic bacteria acquired through diet and environment. Over evolutionary time, the pufferfish has turned this microbial byproduct into a chemical shield, storing it in skin, organs, and sometimes eggs. Tetrodotoxin interferes with sodium channels in nerve cells, blocking the transmission of electrical signals that control muscle movement and respiration. In sufficient doses, it causes paralysis and death. For predators, even a small exposure can be catastrophic. The critical detail is that predators do not need to die to learn this lesson. A bite is often enough. When a predator clamps down on an inflating pufferfish, it may puncture skin or press venomous tissue against sensitive membranes in the mouth. The toxin acts quickly, producing numbness, disorientation, and loss of muscle control. The predator releases the fish not out of mercy, but out of sudden, alarming dysfunction. This experience imprints deeply. Predators that survive such encounters often avoid pufferfish thereafter, recognizing the shape, movement, or even subtle visual cues associated with danger. This is where the pufferfish's strategy becomes uniquely effective. It does not rely on killing predators, it relies on teaching them. In ecological terms, this is an extraordinarily efficient defense. Once a predator has learned to associate pufferfish with pain, confusion, or near death, that knowledge persists. Other pufferfish benefit without ever deploying their defenses. Over time, entire predator populations may avoid them, reshaping feeding patterns across the reef. The toxin thus extends beyond the individual, influencing community behavior through memory and avoidance. Inflation itself carries costs. Expanding the body requires energy and temporarily limits mobility. An inflated pufferfish cannot swim efficiently and is vulnerable if the threat does not retreat quickly. This is why the response is precisely timed. Inflation is not constant. It is triggered only when escape is no longer possible. The fish makes a calculated trade-off, sacrificing movement for deterrence at the exact moment when speed would no longer matter. This timing reflects a deep evolutionary refinement, where defenses are deployed only when they provide maximum return. The predator, now confronted with a spined, toxic sphere, aborts the attack. It pulls away, sometimes violently, shaking its head or retreating in confusion. The reef absorbs this interaction quietly. There is no prolonged chase, no dramatic struggle. The pufferfish remains inflated for several moments longer, ensuring the threat has truly disengaged, then slowly releases the water it ingested. The body contracts back to its original form, spines flattening, posture returning to casual neutrality. Within minutes, it resumes feeding as if nothing has happened. This sequence illustrates a broader principle in marine survival. Not all victories are won through dominance or destruction. Some are achieved through deterrence so complete that conflict becomes unnecessary. The pufferfish does not compete with predators on their terms. It rewrites the terms entirely. By making itself unprofitable, unpleasant, and dangerous to engage, it removes itself from the predator's menu without needing to outfight or outrun anyone. The toxin's presence also influences the pufferfish's own behavior. Knowing that it carries such a powerful defense, the fish can afford to forage more openly and take risks that other species cannot. This access to resources shapes its ecological role. Pufferfish often feed on hard-shelled invertebrates and algae that other fish avoid, using their strong beaks to break down material that would otherwise accumulate and alter reef structure. In this way, their survival strategy feeds back into ecosystem maintenance, linking chemical defense to habitat balance. There is a subtle irony here. The pufferfish's vulnerability is real. Without inflation or toxin, it would be easy prey. Its success depends on predators making a mistake at least once. Curiosity must be punished for the lesson to take hold. In a sense, the pufferfish relies on the intelligence of its enemies. Only predators capable of learning will be deterred long-term. Those that cannot learn often do not survive the encounter. Evolution filters both sides of this interaction, reinforcing cognition as much as physiology. From the camera's perspective, the transformation remains striking every time. The sudden shift from softness to rigidity, from edible to untouchable, encapsulates a survival philosophy rarely appreciated. The pufferfish does not advertise its danger constantly. It waits. It allows the predator to commit. Then it responds in a way that maximizes regret. This regret is the true weapon, spreading through predator populations as avoidance behavior that persists long after the individual encounter. As the reef returns to equilibrium, the pufferfish drifts onward, unremarkable once more. Its round body no longer inflated, its spines flattened, its toxin invisible. Nothing about it now suggests danger, and that is precisely the point. The defense only exists when it is needed. Until then, the pufferfish moves through the ecosystem as a quiet contradiction, a reminder that power in nature does not always look like aggression. Sometimes it looks like an invitation to make the wrong choice. The final image is not one of dominance, but of lesson learned. Somewhere nearby, a predator adjusts its hunting priorities, choosing different prey, altering routes, remembering pain. The pufferfish has not chased it away or killed it. It has reshaped its behavior. In a system built on cause and consequence, that is one of the most effective victories possible. The pufferfish survives not by avoiding attention, but by ensuring that attention once given is never repeated. It wins by making the predator regret curiosity. At first glance, the reef appears calm at its edges, where hard coral gives way to softer architecture and the rigid geometry of stone dissolves into motion. Here, among swaying fronds and fleshy polyps, the sea anemone anchors itself like a misplaced flower, rooted yet alive, unmoving yet lethal. Its tentacles drift with the current, dozens or hundreds of them, elongated and translucent, each one tapering gently toward a rounded tip. In the filtered light they glow faintly, catching plankton and dust as they wave. There is no warning in their movement. They do not snap, coil or tense in anticipation. They simply exist, extended into the water column like an open invitation. To an untrained eye, the anemone looks passive, even fragile. Its body lacks the obvious armor of shells or spines. It does not swim, chase, or flee. It cannot relocate when danger approaches. Instead, it commits fully to its position, embedding its base deep into crevices in the reef or sandy substrate, where it holds fast against currents and storms. This apparent vulnerability is deceptive. The anemone survives not by reacting to threats, but by transforming contact itself into a weapon. Everything about its design assumes that something will eventually touch it, and when that happens, the response is automatic. The tentacles are the first interface, and they are not merely soft appendages. Each one is densely packed with microscopic cells called cnidocytes, specialized structures unique to this ancient lineage of animals. Within each cnidocyte sits a nematocyst, a tightly coiled capsule containing a barbed, hollow thread under extreme internal pressure. This is not venom stored in a gland, waiting to be injected by muscle or intent. It is a mechanical device, preloaded and armed at all times. The anemone does not decide to fire. It does not aim or adjust. The weapon discharges the instant the trigger is touched. As the camera moves closer, the scale of this system becomes apparent. A single tentacle contains thousands of nematocysts, each one independent, each one ready. The trigger is a combination of physical contact and chemical recognition. When soft tissue brushes the tentacle, receptors on the cnidocyte detect both pressure and the presence of biological compounds associated with prey. In response, the capsule explodes outward, firing its thread at astonishing speed. This discharge is one of the fastest cellular processes known, occurring faster than any muscle could possibly contract. The thread penetrates tissue, anchors with its barbs, and delivers venom directly into the cells of the victim. The effectiveness of this system lies in its simplicity. There is no central control to overwhelm or evade. No hesitation, no fatigue. Every tentacle is a field of loaded traps, and touching one often means touching many. For small fish or drifting invertebrates, the result is immediate. The venom disrupts cellular function, causing paralysis or severe distress, while the barbed threads hold the prey in place. The tentacles then begin a slow, coordinated movement, drawing the immobilized organism inward toward the central mouth. The anemone does not rush. The prey is already defeated. Time now works in the anemone's favor. Soft tissue is particularly vulnerable to this attack. Gills, fins, and thin skin offer little resistance to penetrating threads, and the venom spreads quickly through exposed surfaces. Fish that brush an anemone accidentally often flinch violently, muscles spasming as the venom interferes with nerve signaling. Many manage to escape the tentacles, but the damage is done. Even brief contact can impair swimming, disorienting the fish and making it vulnerable to secondary predators lurking nearby. In this way, the anemone influences the reef far beyond its immediate reach, turning a momentary mistake into a cascade of consequences. The reef around the anemone reflects this constant risk. Fish learn to give these zones a wide berth, altering their routes and foraging patterns to avoid the drifting tentacles. The anemone becomes a fixed hazard in the mental maps of reef inhabitants, a place where curiosity is punished without warning. This is why anemones often sit at the boundary between open water and shelter. They guard thresholds, converting transitional spaces into danger zones. The reef, in effect, is studded with living minds that do not pursue, but wait. And yet, within this lethal forest of tentacles, movement continues. A small fish slips between the waving arms, brushing against them without reaction. It darts, pauses, and settles among the tentacles as though they were shelter rather than threat. This is the clownfish, and its presence exposes a remarkable exception to the anemone's rule. Where other fish flinch and flee, the clownfish remains, unharmed, moving freely through a space that should be instantly fatal. The tentacles touch its skin, and nothing fires. This immunity is not innate at birth. Young clownfish approach anemones cautiously, performing a careful acclimation ritual. They make brief contact, retreat, and repeat, gradually coating their skin with a layer of mucus that matches the chemical signature of the anemone itself. This disguise prevents the cnidocytes from recognizing the clownfish as foreign tissue. The trigger is never pulled. The harpoons remain unfired. What appears to be tolerance is, in fact, chemical invisibility. The relationship benefits both parties. The clownfish gains refuge from predators that cannot risk entering the tentacle field, while the anemone receives protection and maintenance. Clownfish chase away butterfly fish and other species that feed on anemone tissue, and their waste products provide nutrients that enhance the anemone's growth. This symbiosis is a rare case where living within a weaponized organism becomes an advantage rather than a liability. It is a reminder that even the most dangerous systems in nature can become safe havens under the right conditions. From an evolutionary perspective, the anemone's reliance on nematocysts represents a different philosophy of predation and defense. Unlike venomous snakes or fish, which must coordinate movement, aim, and delivery, the anemone decentralizes its weaponry. Each tentacle, each cell, is a standalone unit capable of lethal action. Damage to one area does not compromise the whole. This redundancy makes the system resilient. Storms may tear tentacles away. Predators may bite pieces off. The anemone persists, regrowing lost tissue and rearming each new cell as it forms. The energy efficiency of this approach is striking. Once produced, nematocysts require no further investment until they fire. There is no metabolic cost to readiness. The anemone can sit for long periods without feeding, its traps poised indefinitely. When prey does arrive, the cost of firing is repaid by the nutrients gained. This balance allows anemones to thrive in environments where food availability fluctuates and competition is intense. The venom itself is not designed to kill large animals outright. Its primary function is rapid immobilization at the cellular level, disrupting membranes and nerve signaling in small prey. For larger animals, the pain and shock are enough to enforce avoidance. A grazing fish that brushes an anemone once will rarely do so again. Over time, this learning shapes the structure of the reef community, pushing species into different niches and reinforcing the anemone's place as a static but influential predator. As currents shift and light angles change, the anemone remains fixed, its tentacles adjusting passively to the flow. There is no sense of aggression here, no pursuit. The danger exists continuously, evenly distributed across each filament. The reef does not erupt when prey is captured. It barely reacts. A fish disappears slowly into the center of the anemone, its movement stilled, its form absorbed. The tentacles return to their gentle sway, traps reset, as though nothing has happened. This quiet efficiency challenges common perceptions of what danger looks like underwater. There are no teeth, no speed, no dramatic chases. Instead, there is a system built entirely around inevitability. Touch equals consequence. The anemone does not need to recognize prey consciously or respond dynamically. It relies on physics, chemistry, and time. In a world of constant motion, it is the stillness that kills. The irony is subtle but profound. The anemone appears decorative, almost ornamental, blending into the reef's softer palette. Divers admire them for their colors and symmetry, often hovering close to observe their movement. Few realize that they are drifting among one of the most mechanically sophisticated weapon systems in the ocean, scaled down to the microscopic level, but multiplied across every visible surface. The danger is not hidden. It is simply underestimated. As the camera pulls back, the reef resolves into a mosaic of hazards and refuges, of living structures that both sustain and punish. The anemone remains where it has always been, a fixed point of risk around which life rearranges itself. Fish navigate carefully, clownfish weave confidently through forbidden space, and currents carry the scent of countless past encounters. Here, survival is not always about speed or strength. Sometimes it is about knowing which surfaces can be touched and which cannot. The reef, for all its beauty, is not a neutral landscape. It is engineered by its inhabitants, shaped by defenses that fire without warning, and alliances that rewrite the rules of danger. The sea anemone embodies this reality perfectly. It does not chase. It does not threaten. It waits, armed at the cellular level, transforming contact into capture with mechanical certainty. In this ecosystem, the traps do not snap shut. They shoot. The sandy flats at the edge of the reef look deceptively empty, a pale expanse where light ripples across grains and broken shell fragments in slow, hypnotic patterns. This is not the dramatic architecture of coral towers or drop-offs. It is a quieter landscape, shaped by tides and currents, where visibility is wide and danger appears scarce. Fish cruise higher in the water column here, confident in the open sightlines, while the seabed itself seems inert, almost lifeless. But this impression collapses the moment the sand exhales. A faint outline emerges, barely perceptible at first. A soft diamond shape pressed flat against the bottom. The stingray is already here, perfectly integrated into the substrate, its body dusted with sand that clings to its skin like camouflage designed by the environment itself. Only the eyes break the illusion, lifted just enough to scan the world above, while spiracles behind them pulse gently, drawing water in for respiration. The rest of the body is motionless, edges blending seamlessly into the surrounding sediment. In this posture, the stingray is not hiding behind something. It is hiding as something, indistinguishable from the ground it rests on. This buried stillness is not laziness or rest. It is vigilance. Stingrays spend much of their lives in close contact with the seafloor, where they forage for buried invertebrates and avoid predators by minimizing their profile. Their flattened bodies are a product of extreme specialization, with pectoral fins expanded into broad wings that allow them to glide just above the substrate or settle into it completely. This shape reduces drag, conserves energy, and allows them to disappear into the very surface they depend on. But it also creates a vulnerability. When danger approaches from above, the stingray cannot turn to face it quickly. Its mouth is on the underside, its eyes on top, and its body is oriented forward and outward, not upward. Evolution has solved this problem not by repositioning the head, but by weaponizing the tail. Trailing behind the stingray's body is a long, muscular tail, whip-thin compared to the disc of the body, but dense with power. Near its base, or sometimes farther down depending on the species, lies the barb. In silhouette, it looks simple, almost crude, a narrow spike rising along the tail's upper surface. But closer inspection reveals a tool engineered for maximum damage in minimal time. The barb is flattened and serrated along its edges, with backward-facing barbs that resist removal once embedded. Along its surface runs a groove containing venom-producing tissue, sheathed in a thin layer of skin. This is not a passive ornament. It is a blade designed to tear, inject, and retreat in a single motion. The barb exists primarily as a defensive weapon, not a hunting tool. Stingrays do not use it to capture prey. Their diet consists largely of mollusks, crustaceans, and small benthic organisms, which they uncover by flapping their fins to expose hidden animals in the sand. Crushing plates in their mouths do the rest. The tail barb is reserved for moments when the stingray's usual strategies fail, when camouflage is broken or escape is blocked. In those moments, the response is instantaneous and violent. The camera lingers on the tail as the environment shifts. A large shadow passes overhead, perhaps a shark investigating the flat, or a careless human foot descending into shallow water. Pressure waves ripple through the sand, vibrations traveling faster than sight. The stingray detects this not through vision alone, but through a network of sensory cells along its body that register changes in water movement. The ray does not wait to identify the threat fully. In close quarters, hesitation is lethal. The tail lashes upward in a blur, arcing forward over the body in a motion so fast it is difficult to track even in slow motion. This is not a random thrash. It is a precise, practiced strike, driven by powerful muscles at the tail's base that contract with explosive force. The barb sweeps through the water along a curved trajectory, aimed toward whatever looms above the ray's back. In a fraction of a second, the blade connects, puncturing flesh, tearing tissue, and delivering venom deep into the wound. The backward-facing serrations ensure that the damage continues as the barb withdraws, leaving behind a wound that is far more severe than a simple puncture. The speed of this strike is critical. Unlike predators that grapple or bite, the stingray cannot afford prolonged contact. Its body is vulnerable, its gills exposed along the underside, its mobility limited when pressed to the substrate. The tail strike is designed to end the interaction immediately. There is no follow-up attack. There does not need to be. The message is delivered in pain, blood, and shock. The venom amplifies this effect dramatically. Composed of a complex mixture of proteins and enzymes, it causes intense pain, swelling, and tissue damage at the site of injury. The pain is not incidental. It is the primary deterrent. Predators that experience a stingray strike do not need to be killed to be taught. The sensation is overwhelming, often radiating through the affected limb or jaw, disrupting muscle control and triggering a stress response that overrides predatory intent. For large animals, this is enough to abort the attack. For humans, it is a medical emergency characterized by excruciating pain and risk of infection or further injury from retained barb fragments. The structure of the barb itself increases this danger. Because it is serrated and brittle, it can break off inside the wound, leaving fragments that continue to leach venom and complicate healing. This is not an accident of design. It increases the cost of contact even further, turning a single moment of curiosity or aggression into a prolonged ordeal. The stingray does not need to pursue its attacker or defend territory. It only needs to make one point, once. After the strike, the stingray vanishes almost immediately. With a powerful downward beat of its fins, it lifts off the sand and glides away, leaving behind a cloud of sediment that obscures visibility. The flat returns to apparent emptiness, the stage reset. The attacker, if still present, is left to deal with the consequences alone. The stingray does not linger. Survival here depends on disengagement, not dominance. This rear-facing defense shapes the stingray's role in the ecosystem in subtle ways. By occupying shallow flats and sandy channels, stingrays influence how other animals move through these spaces. Predators learn to approach cautiously, if at all. Large fish circle wide, avoiding the telltale outlines of buried rays. Even humans, once stung or warned, alter their behavior, shuffling feet instead of stepping blindly, scanning the sand more carefully. The stingray's presence turns open ground into a zone of conditional risk, altering traffic patterns across the seafloor. From an evolutionary standpoint, the placement of the barb on the tail is significant. It allows the stingray to defend itself without reorienting its body or exposing vital areas. The weapon points backward because the threat usually comes from above or behind, from predators attempting to pin the ray down or bite from the top. Teeth are unnecessary in this equation. Speed, placement, and pain are more reliable. The stingray does not need to win a fight. It needs to make the fight not worth continuing. There is a stark contrast between the stingray's calm demeanor and the violence of its defense. Most of the time, rays move gracefully, wings undulating in slow, fluid motions as they cruise over the seabed. They appear almost gentle, their eyes wide, their movements unhurried. This appearance has misled countless observers into underestimating them. The barb is often out of sight, trailing behind or buried beneath sand, invisible until the moment it is used. This invisibility is part of the strategy. A visible weapon invites caution. A hidden one delivers surprise. The irony is that the stingray would prefer never to use it. Every strike carries risk. A broken barb must be regrown, a process that takes time and resources. Injury to the tail itself could compromise mobility. But when the alternative is being bitten, crushed, or pinned, the calculus is simple. The tail strike exists for moments when all other options are gone. As the camera revisits the sandy flat, the stingray has already resettled somewhere else, half buried once more, eyes scanning, tail relaxed but ready. The environment looks unchanged, but its meaning has shifted. What seemed like open, harmless ground is now understood as a field of potential consequence. Every step, every approach from above, carries the possibility of sudden retaliation. This is the quiet power of the stingray's defense. It does not broadcast danger loudly. It does not posture or threaten. It waits, integrated into the environment, and responds only when necessary, with a precision that leaves no ambiguity. In a world where many predators rely on teeth to seize and hold, the stingray has chosen a different solution. It does not bite. It cuts. The final image is a simple one. The sand smooths over, currents erase the last trace of disturbance, and the flat returns to stillness. Somewhere beneath that surface, a blade waits, angled backward, indifferent to curiosity and unforgiving of contact. The stingray does not need teeth. It has a knife. The reef tightens as depth increases, not into darkness but into complexity. Coral heads crowd closer together, ledges overlap, and shadows layer themselves until open water becomes a series of interrupted corridors. Here, the rules of pursuit change. Speed matters less than access. Bulk becomes a liability. What succeeds in these spaces is not a body built to ram or chase, but one designed to enter, grip, and control. From beneath a slab of coral, the octopus emerges not as a shape, but as a rearrangement of the environment itself. Arms flowing outward like liquid thought, skin shifting color and texture to match stone, algae, and shadow in real time. The octopus does not advertise predation. It does not posture or approach in straight lines. Its body remains soft and compressible, able to pour itself through gaps no wider than its beak, the only rigid structure it cannot fold. This softness is not weakness. It is the foundation of a strategy that replaces impact with contact and replaces speed with certainty. As the octopus advances, it does so with distributed intention. Each arm explores independently, tasting the water with chemoreceptors embedded in its suckers, sampling the chemical traces left by potential prey. Vision contributes, but it is not dominant here. In the maze of the reef, touch and taste arrive first. A crab scuttles along the underside of a ledge, confident in its armor and claws, accustomed to repelling fish that strike and retreat. The octopus does not rush. It positions itself above and slightly behind, aligning arms so that escape routes are quietly removed before the prey understands it is being hunted. This is the critical phase. The octopus hunts not by chasing movement, but by predicting it. Its nervous system, more distributed than centralized, allows each arm to act semi-autonomously, coordinating grip without requiring a single command. The crab senses pressure changes, a disturbance in the water, and raises its claws defensively. It is already too late. The first contact is restraint, not injury. Suckers make contact in rapid succession, dozens of them sealing against shell and joint with controlled force. Each sucker is a muscular sensory organ capable of fine pressure adjustment, allowing the octopus to grip without slipping even on irregular or hard surfaces. This grip is not uniform. It is targeted. Arms wrap around legs, carapace, and any surface that offers leverage. The crab struggles, but struggle only increases the number of contact points. The octopus does not squeeze indiscriminately. It pins. This method is energy efficient and tactically decisive. By immobilizing prey first, the octopus eliminates the risk of counterattack. Crabs can inflict damage with claws, fish with spines or teeth, but only if they can orient their bodies. The octopus denies orientation. Arms pull in different directions, rotating the prey slightly, disorienting it, preventing coordinated resistance. Within seconds, the prey's movements lose structure, becoming frantic rather than strategic. This is the moment the octopus has been engineered to exploit. The beak emerges briefly, tucked beneath the arms like a hidden tool. Unlike the rest of the body, the beak is hard, sharp, and precise, capable of puncturing shell or biting into soft tissue with equal effectiveness. The octopus does not tear or rip. It bites once, accurately, often at a nerve-rich area or a joint where armor is thinnest. For fish, the bite is typically delivered near the base of the skull or behind the eye, where access to the nervous system is greatest. For crabs, it targets points where venom can spread quickly through internal tissues. The venom is not dramatic in presentation, but it is decisive in effect. Delivered through the bite, it begins to interfere with neuromuscular function, reducing the prey's ability to transmit signals between nerves and muscles. The chemistry varies between species, but the outcome is consistent. Resistance fades, muscles weaken, coordination collapses. This is not instant death. It is controlled shutdown. The octopus does not need the prey to die immediately. It needs the struggle to stop. In many cases, suffocation completes the process. As the octopus maintains its grip, arms press against gills or spiracles, limiting water flow. Fish rely on continuous movement of water across gill surfaces to extract oxygen. When that flow is interrupted, oxygen levels drop rapidly. The octopus understands this mechanically, not intellectually. Its arms simply hold in the right places long enough for chemistry and physics to converge. Venom slows the body. Lack of oxygen finishes the work. This combination of restraint first and chemistry second is what makes the octopus such an effective predator across a wide range of prey types. It does not specialize in overpowering any single defense. Instead, it applies a sequence that neutralizes almost everything. Hard shells, sharp spines, rapid swimmers. None of these traits matter once movement is denied. The octopus does not need to outmuscle prey. It needs only to maintain contact. From an ecological perspective, this strategy allows octopuses to occupy a unique role in reef systems. They're not apex predators in the traditional sense, but they exert disproportionate influence. By preying on crabs, mollusks, and fish that other predators avoid or cannot subdue safely, octopuses regulate populations that would otherwise dominate certain niches. Their presence reshapes the balance between grazers, scavengers, and small predators, subtly altering how energy flows through the reef. The octopus's body is optimized for this role in ways that extend beyond arms and venom. Its skin contains chromatophores, iridophores, and leucophores that allow rapid changes in color, brightness, and texture. This camouflage is not just for hiding. It is used during the approach to reduce detection until arms are already within striking distance. Once contact is made, camouflage becomes irrelevant. Control replaces concealment. Internally, the octopus operates with a nervous system unlike that of most animals. A large portion of its neurons reside in its arms rather than its central brain, allowing for rapid, localized decision-making. This architecture supports the kind of multitasking required during a hunt, where several arms must grip, adjust, and respond independently while the beak is positioned for a precise bite. It is a system built for distributed control, perfectly suited to a predator that wins by surrounding rather than striking. There is a quiet irony to this method. To an outside observer, the octopus's kill can look almost gentle. There is no violent thrashing, no blood clouding the water, no explosive impact. The prey simply stops resisting. This visual softness hides the reality of what is happening. The octopus is not being merciful. It is being efficient. Every movement is calibrated to minimize risk and maximize certainty. Once the prey is subdued, the octopus often retreats to a den, carrying its catch beneath its body like a secret. There, it consumes the prey at leisure, sometimes dismantling shells with methodical precision, sometimes injecting digestive enzymes to liquefy tissues before extraction. These remains often accumulate outside dens, forming middens of shells and bones that mark octopus territory long after the animal has moved on. These middens influence the behavior of other reef inhabitants, signaling the presence of a predator that does not chase but waits. The hug is the key metaphor here, and it is an accurate one. The octopus does not seize prey with a single point of force. It envelops. It applies pressure from all sides, turning proximity into inescapability. For prey, animals evolve to escape by sprinting, darting, or snapping back. This is catastrophic. There is no direction to flee when every direction is already occupied. Even predators that attempt to attack octopuses learn quickly that contact cuts both ways. The same arms that restrain prey can redirect attackers, pushing, gripping, and escaping with astonishing control. Combined with ink release and camouflage, the octopus remains one of the few reef animals capable of reversing encounters with larger predators through intelligence and adaptability rather than brute force. As the scene settles, the reef resumes its constant motion. Fish pass through corridors, crabs re-emerge cautiously, and the octopus fades back into the background, its shape dissolving into stone once more. Nothing about the environment suggests that a predation event has just occurred. There is no alarm call, no disturbance echoing through the water. The success of the octopus lies precisely in this quietness. Its victories do not announce themselves. They leave no spectacle, only absence. This is a predator that understands contact better than conflict. It does not rush, does not panic, does not escalate unnecessarily. It waits until it can touch, and once it does, it commits fully. In the crowded geometry of the reef, where speed fails and armor only delays the inevitable, this strategy reigns supreme. The octopus does not need teeth like a shark or a blade like a ray. It needs arms, chemistry, and time. When it reaches you, it does not strike and retreat. It holds. And in that hold, resistance drains away, oxygen dwindles, nerves fall silent, and the reef continues on, indifferent. It hugs you, and you do not come back. The reef narrows where light still reaches, but space no longer belongs to everyone. Coral heads stack closer together, their bases undercut by centuries of currents, forming caves, slots, and shadowed corridors that swallow sound and distort distance. This is architecture, built not for pursuit, but for entrapment. Water moves differently here, slowed and redirected by stone, carrying scent and vibration in unpredictable ways. Fish that enter these spaces do so carefully, bodies angled, fins half-folded, always aware that retreat is harder than advance. It is in these constricted zones that the moray eel becomes less an animal and more a feature of the reef itself. At first, it appears as nothing more than texture. A dark opening in coral, irregular and jagged, lined with what look like pale stones or broken shell fragments. Only when the camera lingers does the illusion break. The stones shift. A mouth opens and closes rhythmically, not in threat, but in respiration, pumping water across gills that sit far back along an elongated body. The teeth are visible even when the jaws are relaxed, long and recurved, designed not for cutting, but for gripping and refusing to let go. The moray does not hide behind the reef. It occupies it, threading its body deep into holes and crevices until rock and muscle become indistinguishable. Moray eels are built for close quarters. Their bodies are laterally compressed and flexible, lacking the rigid fin structures that give many fish speed in open water. Instead, they rely on serpentine motion, using waves of muscular contraction to push backward into holes or forward in sudden lunges. This design sacrifices long-distance pursuit in exchange for control within confined spaces. The moray does not chase prey across the reef. It waits for prey to come close enough that escape routes collapse naturally. The head protrudes just far enough to monitor passing movement. Vision plays a role, but scent is the dominant sense here. Morays possess highly developed olfactory organs, capable of detecting chemical traces carried by the current. A fish swimming past leaves behind a fading trail, and the moray reads it like a map, gauging size, direction, and proximity. This sensory advantage allows the eel to remain still until the exact moment when movement will be most effective. In a habitat where unnecessary motion advertises presence, restraint is power. When the strike comes, it is explosive but brief. The moray lunges forward from its crevice with surprising speed, jaws snapping shut around the prey in a fraction of a second. This is not a prolonged attack. There is no shaking, no tearing, no attempt to subdue in open water. The bite is the beginning of a retreat, not an advance. As soon as the jaws clamp down, the moray reverses direction, pulling its head and captured prey backward into the hole. This backward motion is critical. Most predators attempt to overpower prey by dragging it into open space where leverage and strength can be applied. The moray does the opposite. It drags prey into confinement, into a space specifically chosen because it eliminates resistance. Inside the crevice, the prey cannot turn, cannot accelerate, and cannot deploy defensive maneuvers that rely on space. Fins scrape uselessly against stone. Bodies press against coral walls. Panic replaces coordination. The moray's jaws are not its only weapon. Once the primary jaws secure the prey, a second set of jaws emerges from deep within the throat. These pharyngeal jaws, a rarity among vertebrates, slide forward into the mouth, grip the prey, and pull it further inward. This mechanism solves a problem inherent to eel anatomy. Without strong suction feeding abilities, morays cannot rely on water flow to move prey toward the throat. Instead, they use mechanical transport, actively pulling prey into the esophagus. In the tight confines of a cave, this system becomes devastatingly effective. For the prey, the experience is overwhelming. There is no room to thrash or leverage against the attacker. The walls of the reef become extensions of the moray's grip, bracing the eel's body as it exerts force. This is why the cave itself is the weapon. The moray does not need to overpower prey through raw strength alone. It uses the environment to multiply its effectiveness, turning solid stone into an ally. This strategy explains why morays are such successful predators, despite their apparent limitations. In open water, they would be slow and vulnerable. In caves, they are nearly unbeatable. Fish that rely on speed, schooling, or sudden directional changes find those advantages stripped away the moment they cross the threshold into a crevice. The moray has chosen its battlefield carefully, and everything about its biology supports that choice. The reef reflects this dynamic subtly but persistently. Small fish dart past cave entrances with heightened caution, maintaining greater distances than they would from open coral. Many species learn to recognize the silhouette of a moray's head, the telltale gape and exposed teeth signaling danger even in stillness. Some fish engage in cooperative hunting with morays, exploiting their ability to flush prey from hiding places in exchange for access to food. This complex interaction highlights the moray's role not just as a predator, but as an architect of behavior across the reef community. Physiologically, the moray's skin also contributes to its success. Thick, mucus-coated, and lacking the scales of many fish, it resists abrasion as the eel presses against sharp coral and rock. This protective layer reduces injury and infection in an environment filled with abrasive surfaces. The elongated body allows force to be distributed along the length of the eel rather than concentrated at a single point, making it easier to brace against the cave walls during a struggle. There is an earned irony in how fearsome morays appear compared to how they actually hunt. Their perpetual open mouth has given them a reputation for aggression, but this gape is simply a necessity for respiration, not a threat display. Morays are not impulsive attackers. They do not patrol the reef looking for conflict. Their violence is situational, triggered only when prey enters a zone where escape is mathematically unlikely. The aggression is precise, not emotional. Once the prey is secured deep within the crevice, the moray consumes it methodically. Large prey may be torn into manageable pieces using leverage against the rock, smaller prey swallowed whole. The remains rarely drift far from the cave, further reinforcing the area as a focal point of predation. Over time, these feeding sites influence the distribution of fish across the reef, creating invisible boundaries shaped by risk rather than physical barriers. For humans, encounters with morays are often misinterpreted. Bites typically occur when divers place hands into holes without visibility, mistaking a moray's home for empty space. The eel reacts not with pursuit, but with the same close-range defense it uses on prey. Clamp, retreat, hold. The injury is often severe, not because the moray is malicious, but because its teeth are designed to grip and refuse release. Again, the cave amplifies the danger. In tight spaces, there is no room to pull away cleanly. As the camera pulls back, the reef resumes its layered calm. Fish resume their patrols, currents carry plankton through corridors, and the cave entrance returns to apparent emptiness. Only the faint rhythm of a breathing mouth gives away the presence of the predator within. The moray waits, patient and still, a living extension of the stone. This is predation without pursuit, violence without spectacle. The moray eel does not need speed, venom, or elaborate traps. It needs proximity and architecture. By choosing to live where space itself becomes restrictive, it transforms the reef into a device that favors its every move. Prey do not lose because they are weak. They lose because they entered a space where strength no longer matters. The reef is often described as a place of beauty and abundance, but it is also a place of thresholds. Cross the wrong one, and the environment itself turns hostile. For the moray eel, this is the ultimate advantage. It does not hunt the reef. It lets the reef do the hunting for it. When the jaws snap shut and the body retreats into darkness, the outcome is decided not by the eel alone, but by the stone, the angles, and the absence of space. Teeth are only the beginning. The true weapon closes around the prey from all sides. The cave is the weapon. The reef floor hardens as depth and turbulence increase, trading soft sand for rubble and limestone plates fractured by time and wave energy. This is a landscape shaped by impact. Broken coral skeletons grind against one another, shells accumulate in pockets, and every surface bears the scars of compression, abrasion, and force. Here, strength is measured not by speed or size, but by the ability to withstand repeated mechanical stress. Many animals avoid these zones entirely. Those that remain either hide, scavenge, or armor themselves heavily. One resident does neither. It builds, waits, and strikes with a violence so precise that it briefly turns water itself into a weapon. The mantis shrimp does not announce its presence. Its burrow is little more than a reinforced tunnel in the reef, lined with rubble carefully selected and positioned. The entrance is often ringed with shell fragments and stone chips, evidence not of feeding alone, but of engineering. This animal is not wandering the reef looking for opportunity. It is anchoring itself to a specific point, transforming a small patch of seafloor into a controlled arena. From this position, the mantis shrimp watches with eyes unlike any other. Mounted on stalks, each eye rotates independently, capable of perceiving depth, motion, and polarization in ways that defy simple comparison. The mantis shrimp does not merely see color. It interprets the physical properties of light itself, extracting information invisible to most reef inhabitants. This sensory advantage allows it to detect subtle changes in movement and material, distinguishing living tissue from shell, threat from opportunity. In a cluttered environment where milliseconds matter, perception is the first rule breaker. The body remains tucked within the burrow, only the eyes and the front segments visible. The raptorial appendages, folded tightly beneath the head, are hidden from view. These limbs are the focus of the mantis shrimp's reputation, but they are often misunderstood. They are not claws in the traditional sense, nor are they venom delivery systems. In smashing species, these appendages terminate in a calcified club, layered with mineralized structures designed to absorb and redirect stress. This club is not sharpened. It is hardened. The goal is not cutting. It is impact. The prey enters the frame slowly. A crab edges across the rubble, confident in its shell, accustomed to resisting the bites of fish and the probing attacks of octopuses. Armor has served it well. Shell thickness increases with age, reinforced by calcium carbonate deposited in layered plates. To most predators, this is a deterrent. To the mantis shrimp, it is a target. The strike begins before the prey realizes it is being hunted. Muscles within the mantis shrimp's appendage contract and lock, storing energy in elastic structures much like a drawn bow or compressed spring. This loading phase is brief but critical. The shrimp is not winding up. It is charging. When the latch releases, the club accelerates forward with astonishing speed, reaching velocities comparable to a projectile. The appendage does not swing. It snaps. The impact is immediate and catastrophic. The club connects with the shell, delivering a force sufficient to fracture mineralized armor that evolved to resist crushing jaws. But the strike does not end there. As the club decelerates abruptly upon impact, it generates a localized drop in pressure in the surrounding water. This pressure differential causes water to vaporize momentarily, forming a cavitation bubble at the point of contact. This bubble is not metaphorical. It is a physical void created by the extreme conditions of the strike. Almost instantly, the bubble collapses. Water rushes back in, slamming into the surface with additional force and generating a secondary shock wave. For a brief moment, temperatures spike and light may flash, a phenomenon known as sonoluminescence. The prey experiences not one attack, but two. First, the mechanical blow of the club. Then, the collapse of water itself. This is why the mantis shrimp's punch breaks the rules. Most predators rely on either physical damage or chemical disruption. Venom interferes with nerves or muscles. Teeth tear and cut. The mantis shrimp does neither. It weaponizes physics. The cavitation collapse delivers damage even if the initial strike misses slightly or glances off. Shells crack not only from direct force, but from internal shock, stress fractures propagating through the material faster than the crab can respond. The phrase chemical warfare without chemicals is not exaggeration. The mantis shrimp achieves effects comparable to toxins by manipulating the physical environment at microscopic scales. Water becomes the delivery system. Pressure becomes the weapon. The prey's biology is irrelevant once the structural integrity of its armor fails. The crab stops moving not because it has been poisoned, but because the system that protects it has been compromised violently and instantaneously. The mantis shrimp often strikes multiple times in rapid succession, each blow precisely targeted. It does not flail or overcommit. The appendage retracts, reloads, and fires again, using the burrow entrance as a stable platform. The surrounding stone absorbs recoil, allowing maximum energy transfer forward. This interaction between animal and environment is crucial. The mantis shrimp does not fight in open water. It fights from cover, braced against the reef, turning its home into a firing position. Once the shell is breached, the outcome is inevitable. Soft tissue is exposed, and the mantis shrimp can feed at leisure, breaking the prey apart or pulling it into the burrow. The violence of the encounter contrasts sharply with what follows. Feeding is methodical, almost calm. The energy expenditure is front-loaded into the strike. After that, the system resets. This strategy shapes the ecosystem in subtle but far-reaching ways. By preying on heavily armored organisms, mantis shrimp regulate populations that would otherwise dominate rubble zones. Snails, crabs, and bivalves all fall within its reach, altering competition for space and resources. The presence of mantis shrimp creates areas where shell strength alone is no guarantee of survival, forcing prey species to adapt behaviorally rather than structurally. Some avoid these zones entirely. Others shift activity patterns, emerging at times when mantis shrimp are less active. The mantis shrimp itself is constrained by its specialization. The same appendages that deliver devastating blows are vulnerable to damage if used improperly. Repeated impacts generate stress, and while the club is reinforced with a complex arrangement of fibers that prevent catastrophic failure, it still requires careful use. This is why the shrimp is selective. It does not strike randomly. It chooses moments when success is likely, conserving energy and minimizing wear. There is an irony in how this animal is perceived. Its small size invites underestimation. Its bright colors suggest vulnerability or display rather than lethality. Yet in mechanical terms, it outperforms many much larger predators. Aquariums learn this lesson quickly when mantis shrimp shatter glass with exploratory strikes, not out of aggression, but because the material responds to force the way shells do. The mantis shrimp does not recognize boundaries the way humans do. It recognizes resistance. From a physiological standpoint, The mantis shrimp represents an extreme endpoint of evolutionary experimentation. Muscles, joints, and exoskeleton have been tuned not for endurance, but for peak output over microscopic timeframes. Energy is stored elastically, released explosively, and dissipated through materials engineered to survive repeated stress. The animal itself becomes a living demonstration of how biological systems can exploit physical laws rather than compete within biological limits. As the camera slows the strike, the impossible becomes visible. The club blurs. The bubble forms. The collapse ripples outward. The prey's shell fractures along lines that mirror geological faulting more than animal predation. This is not a bite. It is an event. A localized catastrophe delivered with surgical precision. Afterward, the reef returns to its baseline state. Particles drift. Other animals resume movement. The mantis shrimp retreats into its burrow, eyes still scanning, appendages folded once more. Nothing about its posture suggests recent violence. The system is reset, ready to repeat. The mantis shrimp does not chase prey. It does not stalk over distance. It waits, anchored, patient, its power condensed into a single motion that redefines what a strike can be. In a world where most weapons are biological, it brings physics to the fight. No venom, no poison, just force, pressure, and timing, so exact that water itself becomes an accomplice. The final image lingers on the cracked shell, fragments settling into the rubble like any other debris. There is no lingering toxin, no chemical trace. Only the memory of impact encoded in broken structure. The mantis shrimp does not need to hit twice to win, but it often does. First, the club connects. Then the water follows. It hits once, then water hits again. The reef edge where stone meets shadow is a place built on hard decisions. Crevices cut deep into limestone, forming narrow corridors that widen suddenly into chambers, then constrict again without warning. Light reaches these spaces reluctantly, bending around corners and dissolving into dim gradients that favor animals built for patience rather than speed. Here, armor feels like a sensible investment. Shells resist bites. Hard edges deflect teeth. Weight anchors bodies against surge and current. In this environment, the lobster appears well prepared, a walking fortress designed to survive a world of crushing jaws and sudden strikes. Its body is encased in a thick exoskeleton, layered and reinforced with calcium compounds that harden over time. Each segment interlocks with the next, forming a suit that resists puncture and disperses force. The claws, oversized and asymmetrical, are raised slightly as the lobster moves, not in aggression but readiness. One claw is heavier, built for crushing, capable of breaking shells and bone through slow, overwhelming pressure. The other is narrower and faster, adapted for slicing and gripping, a precision tool rather than a blunt instrument. Together, they form a versatile defense and feeding system that has served lobsters well for millions of years. When threatened, the lobster does not flee blindly into open water. It backs toward cover, antennae sweeping wide to feel for obstacles, tail tucked beneath the body, claws angled outward. Retreat is controlled and deliberate. The goal is not distance, but geometry. A narrow crevice transforms the lobster's bulk from liability into advantage. Inside confined space, its armor blocks access to vital areas. Claws can brace against rock, and attackers lose the ability to circle or strike from behind. This is the bunker strategy, and against many predators, it works. Fish that rely on speed hesitate at the threshold. Sharks and large reef predators cannot fit their heads inside without exposing eyes and gills to snapping claws. Even strong jaws struggle to gain leverage against a shell pressed firmly against stone. The lobster becomes part of the reef itself, wedged into place, immovable without significant effort. For a time, the crevice is safety. But armor is not invisibility, and bunkers are invitations to specialists. As the camera drifts wider, the environment reveals its next layer of threat. The same crevices that protect lobsters also guide predators that have evolved to exploit confinement. An octopus glides along the rock face, arms exploring independently, tasting the water with suckers that read chemistry more clearly than sight ever could. Nearby, the dark head of a moray eel protrudes from another hole, jaws opening and closing rhythmically, sampling scent trails carried by the current. These predators are not discouraged by armor. They are attracted by it. The lobster's shell advertises certainty. Inside is a slow, nutrient-rich meal that cannot sprint away. For hunters that specialize in leverage, restraint, and extraction, armor is not a deterrent. It is a signal that the prey will not escape easily once contact is made. Evolution has turned the lobster's greatest strength into a filtering mechanism, excluding weak predators while drawing in the ones most capable of killing it. The octopus approaches first, not with urgency, but calculation. It understands space intuitively, recognizing that the crevice funnels movement and limits options. The lobster senses disturbance through vibrations in the water and raises its claws fully now, presenting their full span to block the entrance. This posture is effective against most fish. Against an octopus, it is simply another surface to grip. Arms slide forward, suckers attaching to shell and rock with quiet precision. The octopus does not rush the claws. It does not need to. Instead, it pins the lobster against the back of the crevice, applying pressure from multiple angles at once. The lobster pushes back, muscles straining, claws snapping reflexively. But there is no clean target. Every movement meets resistance. The bunker that once provided security now becomes a constraint, preventing the lobster from turning or retreating further. Armor delays the outcome, but it does not change the direction. The octopus applies its beak only when the lobster's movements slow, delivering a precise bite where shell plates meet, injecting venom that interferes with neuromuscular function. The lobster's claws lose coordination, power fading unevenly. The crevice that once shielded it now ensures there is nowhere to fall, nowhere to drift out of reach. The bunker has become a holding cell. If the octopus fails or chooses not to commit, the moray eel presents a different solution. Where the octopus envelops, the moray clamps. The eel does not attempt to pull the lobster out into open water. Instead, it bites onto a limb or carapace edge and reverses, dragging the lobster deeper into overlapping tunnels where leverage increases. Inside these spaces, the lobster's size works against it. Claws scrape uselessly against stone. The tail cannot flick effectively. Armor protects against teeth but does nothing to prevent being repositioned. Morays possess pharyngeal jaws that reach forward from the throat, gripping prey and pulling it inward. Against armored animals, this mechanism allows the eel to apply force without relying on suction or bite strength alone. Piece by piece, limb by limb, the lobster is broken down, not by penetration, but by extraction. The armor remains largely intact until the end. It is the joints, the seams, the points of articulation that fail first. This is the paradox of defensive design. Armor does not eliminate vulnerability. It relocates it. The thicker the shell, the more predictable the weak points become. Specialized predators learn these points intimately, refining techniques that bypass strength entirely. Over evolutionary time, this creates an arms race not of thickness versus force, but of intelligence versus structure. The lobster's claws illustrate this trade-off perfectly. The crusher claw, slow but powerful, excels at feeding on hard prey like mollusks. The cutter claw, faster and sharper, handles softer tissue and precision tasks. Together, they make the lobster a formidable forager and a capable defender. But both claws require space to operate. Inside a narrow crevice, their range of motion collapses. They become obstacles rather than weapons, blocking escape and limiting flexibility. The reef is filled with these contradictions. Structures that protect in one context become traps in another. The lobster's instinct to seek cover is sound, but not universally safe. It assumes attackers that are larger, faster, and less flexible. It does not account for hunters that think in terms of angles, grip, and patience. Armor also carries metabolic costs. Growing and maintaining a heavy exoskeleton requires energy and resources. During molting periods, when the old shell is shed and a new one hardens, lobsters are at their most vulnerable. They hide even more aggressively during these times, retreating deep into crevices and remaining inactive. Ironically, this behavior increases exposure to the very predators most capable of exploiting confined space. The need to hide creates predictability. Predictability invites attention. From an ecological perspective, lobsters occupy an important role as both predators and prey. They regulate populations of smaller invertebrates, influencing reef composition and nutrient cycling. At the same time, they provide high-value meals for octopuses, morays, and larger fish that can overcome their defenses. This balance maintains diversity by preventing any one strategy from dominating. Armor alone is not enough. Speed alone is not enough. Intelligence alone is not enough. Survival emerges from trade-offs, not absolutes. The reef reflects this balance in subtle ways. Crevices with high lobster density often show signs of octopus activity, middens of shell fragments accumulating nearby. Moray dens cluster around similar zones, drawn by reliable prey traffic. Over time, these interactions shape the microgeography of the reef, turning certain structures into hotspots of predation rather than refuge. There is a quiet lesson embedded here, one that extends beyond lobsters themselves. Defense strategies do not exist in isolation. They are evaluated constantly by other organisms, tested, exploited, and adapted against. What works against one threat invites another. The lobster's armor filters its enemies, removing the unqualified and summoning the specialists. As the camera pulls back, the scene resolves into stillness again. The crevice looks unchanged, its entrance dark and unremarkable. Somewhere inside, a shell may remain, cracked or intact, evidence of a transaction that reshaped the energy flow of the reef. Elsewhere, a lobster backs cautiously into another hole, claws raised, repeating a strategy that has worked often enough to persist. This repetition is not failure. It is the nature of evolution operating under constraint. Lobsters survive not because their armor makes them invincible, but because it keeps them alive long enough, often enough, to reproduce before the wrong predator arrives. Most deaths in nature are not prevented. They are postponed. The reef does not reward perfection. It rewards adequacy under pressure. Armor buys time. It reduces the number of predators that can kill you, but it does not eliminate death. It changes the terms, narrowing the field until only the most capable remain. The final image lingers on the crevice mouth, empty now, currents carrying faint chemical traces through stone corridors. Somewhere nearby, an octopus explores with patient arms. A moray samples the water with rhythmic breaths. The lobster's armor did exactly what it was meant to do. It stopped most threats. It just could not stop the right ones. Armor does not stop death. It changes who kills you. The reef's scavenging zones are never quiet. They lie just beyond the clean edges of coral gardens, where structure breaks down into rubble, broken shells, and drifting organic debris. This is where things end up after the drama is over. Fragments of crushed armor, half-consumed carcasses, discarded molts, and sinking scraps accumulate here, carried by currents and gravity into shallow depressions and channels. Life converges on these places not because they are beautiful, but because they are profitable. Nutrients linger. Calories are easier to find. And among the first to arrive are the crabs. They emerge from every direction, climbing over stone and coral with sideways precision, antennae flicking, legs probing, eyes elevated just enough to scan for rivals and danger. Crabs are not subtle feeders. They pull, tear, and pry, claws working constantly as they compete for access to whatever the reef has left behind. A dead fish, a discarded shellfish, the remains of a predator's meal, all are fair game. Their armor protects them from many immediate threats, allowing them to feed openly where softer-bodied scavengers would hesitate. In these moments, the crabs appear successful, efficient, well adapted to a system that rewards opportunism. But this abundance hides a quieter danger. Not all food in the reef is neutral. Some prey carries chemical defenses that do not disappear when the animal dies. Toxins designed to deter predators while alive can persist in tissue long after movement stops. Venom, defensive poisons, and bioaccumulated compounds linger invisibly, woven into muscle, organs, and skin. When crabs scavenge indiscriminately, they ingest more than calories. They ingest history. Every bite is a chemical record of where that prey has been and what it has eaten. The crab does not know this. Its sensory world is dominated by texture and movement, not molecular composition. A dead pufferfish does not announce its danger once still. A toxic snail looks no different from a harmless one once cracked open. Even pieces of animals killed by venomous predators may still contain active compounds, redistributed through tissue during the struggle. To a scavenger built to exploit leftovers quickly, caution is a luxury it cannot afford. As crabs feed, toxins move. This is not poisoning in the dramatic sense. There is no immediate collapse, no sudden paralysis, no visible reaction at the moment of contact. Instead, compounds accumulate gradually, passing from prey into scavenger, sometimes stored in tissues without obvious effect. Crabs are surprisingly tolerant of many toxins, their physiology capable of handling chemical stress that would incapacitate more sensitive animals. This tolerance allows them to function as chemical carriers, absorbing substances that remain biologically active long after ingestion. The reef does not register this process visually. It unfolds at scales too small and too slow to see, yet it shapes behavior all the same. Predators that hunt crabs do not always learn through direct injury. They learn through consequence. A fish that consumes several toxin-laden crabs may experience weakness, impaired coordination, or reduced feeding efficiency. The symptoms are subtle, easily mistaken for stress or illness. Over time, these effects influence survival. Predators that regularly target scavengers in high-risk zones may grow slower, hunt less effectively, or become more vulnerable to their own enemies. The toxin does not need to kill to exert pressure. It only needs to tilt the balance. This is how venom zones form without borders or warning signs. Certain areas of the reef become chemically loaded, not because venomous animals dominate them, but because their remains pass through them. Where toxic species are common, scavengers ingest more chemical defenses. Where scavengers concentrate, those compounds move upward again. The result is a diffuse, shifting field of risk that follows behavior rather than geography. A crab feeding frenzy is not just a contest for food. It is a point of chemical exchange, redistributing toxins through the local food web. Crabs themselves respond to this pressure indirectly. Competition intensifies in these zones because food is unpredictable. Some items are safe, others are costly. Yet the crabs cannot tell which is which. Their solution is speed and volume. Eat quickly, eat often, move on. This behavior increases turnover, spreading toxins across individuals rather than concentrating them in one. In ecological terms, this dilution strategy reduces the chance that any single crab will accumulate a lethal dose, even as the population as a whole carries more chemical risk. The reef's predators adapt in parallel. Some avoid scavenging crabs entirely, focusing on live prey with more predictable chemistry. Others develop tolerances of their own, gradually adjusting physiology to handle low levels of toxins. These adaptations are rarely perfect. They come with trade-offs in metabolism, growth, or reproduction, but they allow certain species to exploit food sources others cannot, reinforcing specialization and partitioning the ecosystem along invisible chemical lines. There is a deeper irony here. Venom and toxin defenses evolved primarily as immediate deterrents, meant to discourage attack at the moment of contact. Yet in death, those same defenses gain a second life. They influence the reef not through fear, but through consumption. The weapon outlives the animal, reshaping interactions long after the original encounter has ended. This is especially evident near species known for powerful chemical defenses. Pufferfish, toxic nudibranchs, certain sponges, and venomous fishes all contribute to this background toxicity. When they die naturally, are partially eaten, or discarded by predators that cannot finish them safely, their tissues enter the scavenger economy. Crabs do not discriminate. They dismantle, distribute, and redistribute these compounds, acting as intermediaries in a system where danger is no longer tied to teeth or stingers. From a physiological perspective, this process exposes a fundamental vulnerability in predators. Digestion is not neutral. The gut is a gateway, and not everything that passes through it is inert. Defensive toxins often target nerve function, muscle contraction, or cellular respiration, the same systems predators rely on for hunting and escape. Even sublethal exposure can alter behavior in ways that reduce fitness. Slower reaction times, less precise strikes, poorer judgment. In a reef where margins are thin, these changes matter. Crabs, meanwhile, continue their role largely unaffected in the short term. Their armor and robust metabolism buffer them from many of these effects. This asymmetry creates a subtle inversion of power. The animal lowest in the hierarchy, the scavenger picking at scraps, becomes a vector that weakens animals higher up the chain. Not intentionally, not strategically, but inevitably. This dynamic challenges simple views of predation. Danger does not always flow from top to bottom. It can move sideways and upward, carried by bodies that were never meant to be weapons. A crab does not need venom glands or stingers to be dangerous. It only needs to eat in the wrong place at the wrong time and be eaten later. The reef structure amplifies this effect. Scavenging zones often coincide with crevices and rubble fields where predators hunt and retreat. A moray eel that consumes crabs regularly may accumulate toxins indirectly, compounding the stress already placed on its system by a high-protein diet. An octopus feeding heavily in these areas may experience reduced efficiency, pushing it to hunt more aggressively or target different prey. These shifts ripple outward, altering patterns of predation and competition across the reef. Nothing about this process is visible to casual observation. There is no dramatic event to mark it. No single death that explains the pattern. Instead, the reef's chemistry quietly shapes outcomes, favoring some strategies over others, nudging populations in directions that seem unrelated to venom or poison at first glance. This is why scavengers are so important to ecosystem dynamics. They are not just cleaners. They are conduits. By breaking down and redistributing matter, they ensure that no defense remains localized. Everything spreads. Everything returns. In doing so, they transform individual survival strategies into community-level consequences. As the camera lingers on the crabs, still fighting over scraps, the scene appears almost mundane. Claws clash. Pieces are torn free. One crab retreats with a prize, another advances to claim what remains. Yet beneath this surface activity, a slower process is unfolding. One that does not announce itself. Molecules move, compounds accumulate, risk shifts. The reef is often portrayed as a place where danger is obvious and immediate, marked by teeth, speed, and venomous strikes. But much of its threat operates on delay. The most effective weapons are not always delivered in the moment of attack. Sometimes they wait, hidden in tissue, passed hand to hand, meal to meal, until they reach an animal that never saw them coming. The crabs finish feeding and scatter back into the rubble, their armor once again just armor, their claws just tools. Somewhere above, a predator chooses its next target, unaware that the risk it faces has less to do with the prey's ability to fight back and more to do with what that prey consumed hours or days earlier. In this ecosystem, danger does not always bite or sting. Sometimes it is swallowed quietly and carried forward, altering outcomes without spectacle or sound. The reef does not need constant violence to enforce its rules. It needs memory, chemistry, and time. Sometimes the weapon is not the bite. It is what you ate. The reef brightens where hard coral gives way to living color, where motion becomes ornamental, and danger disguises itself as beauty. Sunlight fractures into ribbons as it passes through shallow water, illuminating a cluster of sea anemones anchored firmly to rock and rubble. Their tentacles pulse gently with the surge, translucent and inviting, a field of soft motion that looks more decorative than defensive. Around them, fish slow their pace, instinctively adjusting their distance. This is not empty space. It is claimed ground. And in the center of it, no larger than a human hand, a clownfish hovers with unmistakable confidence. The clownfish should not be brave. Its body is small, laterally compressed, and ill-suited to speed or force. Its fins are built for maneuverability, not endurance, and its bite carries no threat to animals many times its size. In open water, it would be easy prey, dismissed quickly by predators that measure danger in mass and momentum. Yet here, within arm's reach of the anemone, the clownfish behaves like something far larger. It darts forward aggressively, snapping and charging at intruders that drift too close. Larger fish flinch and turn away, surprised not by the clownfish's strength, but by its certainty. That certainty does not come from the clownfish alone. It is borrowed. The anemone behind it is not scenery. It is infrastructure. Each tentacle is armed with thousands of nematocysts, microscopic harpoons that fire automatically upon contact, injecting venom into soft tissue with mechanical precision. Fish that brush against these tentacles by accident recoil violently, often disoriented, sometimes paralyzed. Predators learn quickly that the cost of approaching too closely is not worth the reward. The anemone does not chase or threaten. It waits. It transforms proximity into consequence. For most fish, this is an exclusion zone. For the clownfish, it is home. The relationship between clownfish and anemone is not accidental, nor is it simple tolerance. It is a negotiated alliance shaped by chemistry, behavior, and time. A juvenile clownfish approaching an anemone for the first time does not swim straight in. It performs a cautious ritual, making brief, deliberate contact with the tentacles, retreating and repeating the process over hours or days. With each touch, it coats its skin in the anemone's mucus, altering its chemical signature until the nematocysts no longer recognize it as foreign. The harpoons remain armed, but the trigger is never pulled. This chemical camouflage is the foundation of the symbiosis. Once established, it allows the clownfish to move freely among the tentacles, immune to a weapon system lethal to nearly everything else on the reef. The anemone does not turn its stingers off. It simply cannot see the clownfish as a target. Shelter is the most obvious benefit. When threatened, the clownfish retreats instantly into the tentacle field, where predators cannot follow without injury. But the advantage goes beyond passive protection. The anemone becomes a staging ground from which the clownfish can act offensively. This is why the charging behavior matters. The clownfish does not wait to be attacked. It patrols the perimeter of its anemone, driving away fish many times its size with sudden lunges and rapid snaps. The message is not that the clownfish is dangerous. The message is that the space behind it is. Predators interpret this quickly. A charge from open water might be bluff. A charge from the mouth of a venomous fortress is not. One wrong movement, one misjudged pursuit, and the predator finds itself brushing against tentacles that fire without mercy. The clownfish exploits this hesitation relentlessly, positioning itself between the intruder and the anemone, daring it to advance. Most do not. Aggression in this context is not a personality trait. It is an ecological strategy enabled by backup. The clownfish behaves boldly because it can retreat instantly into safety. This confidence alters the flow of energy around the anemone. Fish that might otherwise graze nearby keep their distance. Predators learn to hunt elsewhere. The immediate area becomes quieter, less contested, more stable. The anemone gains a buffer zone, enforced not by its own reach alone, but by the behavior of its resident fish. The anemone benefits in other ways as well. Clownfish are not passive tenants. As they move among the tentacles, they remove debris, parasites, and sediment that could otherwise smother the anemone's surface. Their constant motion improves water circulation around the anemone's body, increasing oxygen availability and waste removal. Their waste products provide nutrients, particularly nitrogen, that enhance anemone growth and reproduction. In some cases, clownfish even lure prey toward the anemone through their movement, increasing feeding opportunities. This exchange of services stabilizes both partners. The anemone grows larger and healthier, expanding its tentacle field and defensive reach. The clownfish gains a more formidable refuge and a more valuable territory to defend. Over time, this feedback loop reinforces the relationship, making established anemone-clownfish pairs some of the most stable micro-communities on the reef. The broader ecosystem responds to this stability. areas around anemones often host higher densities of small invertebrates and algae, benefiting from reduced grazing pressure by larger fish. Other species learn to navigate these zones carefully, exploiting the margins without triggering defensive responses. The anemone becomes a fixed reference point in the reef's social geography, a place where rules change abruptly at an invisible boundary. Physiologically, the clownfish's tolerance of anemone venom represents a remarkable adaptation. Its skin mucus is not static. It must be maintained continuously, replenished as cells slough off and environmental conditions change. Stress, injury, or prolonged absence from the anemone can disrupt this protective layer, temporarily increasing vulnerability. This is why clownfish rarely stray far from their host. The fortress only protects those who stay within range. There is also hierarchy within this system. Clownfish groups are typically structured around a dominant breeding pair, with smaller individuals occupying subordinate roles. Aggression is directed not only outward, but inward, maintaining order and access to the anemone. This social structure ensures that only a limited number of fish share the protection, preventing overcrowding that could strain the anemone or dilute its benefits. Even here, safety is rationed. The irony is subtle but telling. The clownfish is often celebrated as gentle or harmless, its bright colors and rounded shape evoking innocence. Yet in ecological terms, it is an enforcer. It polices territory, excludes competitors, and leverages venom. It does not possess to dominate space it could never hold alone. Its success is not about strength, but about alliance. This dynamic highlights a broader truth about survival on the reef. Power is rarely isolated. It is often borrowed, shared, or outsourced. The clownfish does not need its own toxin. It needs access to someone else's. In return, it provides services that make that toxin more effective and more secure. This mutual reinforcement allows both species to thrive in an environment where solitary strategies often fail. As the camera pulls back, a larger fish approaches again, testing the boundary. The clownfish charges without hesitation, fins flared, body vibrating with urgency. The intruder veers away at the last moment, unwilling to gamble against invisible stingers. The anemone's tentacles continue their gentle sway, indifferent to the exchange. The fortress holds. Nothing about this interaction is dramatic in isolation. There is no contact, no injury, no visible violence. Yet it is decisive. Territory is defended. Resources are secured. The balance of the reef shifts slightly, guided by an alliance small enough to overlook and powerful enough to shape behavior. The clownfish returns to hover among the tentacles, confidence restored, patrol resumed. It is still small. It is still fragile away from this place. But here, backed by venom it does not produce and weapons it cannot fire, it stands its ground against a world that would otherwise consume it. In the layered logic of the reef, this is not cheating. It is cooperation refined by evolution. The anemone offers poison. The clownfish offers vigilance, maintenance, and defense. Together they create a zone where size no longer determines authority. Small fish, big bodyguard. The reef floor here slopes gently, a mosaic of sand patches, coral heads, and low ledges carved by currents that never quite stop moving. It is a place where motion is constant but rarely fast, where survival depends less on sprinting than on timing. Fish drift between cover and open water, adjusting their distance from the bottom by instinct, always aware that the space beneath them is not empty. Sand lifts and settles in faint pulses as buried organisms shift and breathe. This is not a battlefield in the dramatic sense. It is a pressure zone, and in pressure zones, speed is often irrelevant. A shadow detaches itself from the reef, not abruptly, but with a slow, deliberate certainty. The grouper emerges as mass before form, a thick-bodied presence whose outline blends with rock until it moves just enough to reveal intention. Groupers are not sleek. Their bodies are heavy, laterally compressed, and built around a wide skull and cavernous mouth. Their fins are strong but not fast, designed for short bursts of repositioning rather than sustained pursuit. Nothing about the grouper suggests a hunter that chases. That is because it does not need to. The grouper settles again, hovering inches above the seabed, pectoral fins making small, almost lazy adjustments to hold position. Its eyes track movement constantly, rotating slightly, independent enough to scan different planes of the reef. Vision matters here, but not in the way it does for predators that rely on distance. The grouper is watching for proximity, not trajectory. It is measuring how close is too close. Reefs are crowded with animals that believe speed is their greatest defense. Small fish dart, hover, and pivot, trusting that a rapid burst of movement will carry them out of danger before jaws can close. In open water, this logic often works. In structured environments like reefs, it fails catastrophically. The grouper has evolved to exploit that failure with a method so fast that it bypasses reaction entirely. The prey enters the frame as a flicker of silver, a small fish pecking at sand grains stirred by unseen invertebrates. It is focused downward, attention narrowed to food. The grouper does not move toward it. Instead, it aligns its body, subtle adjustments bringing its mouth directly in line with the prey. This alignment is critical. The grouper is not aiming to bite. It is preparing to inhale. The strike is not a lunge in the traditional sense. There is no forward rush, no snapping jaws closing on flesh. Instead, the grouper opens its mouth with astonishing speed, expanding the buccal cavity so rapidly that it creates a powerful pressure differential. Water rushes inward, dragging everything in front of the mouth with it. Sand erupts from the seabed in a sudden funnel, grains lifting and spiraling as if pulled by an invisible force. The prey vanishes into the expanding void before its muscles even receive the signal to flee. This is suction feeding at its most extreme, a biological solution that replaces pursuit with physics. The grouper does not need venom because the prey is never given the chance to resist. The entire interaction unfolds in milliseconds, faster than most nervous systems can process danger. By the time the prey understands what is happening, it is already inside the mouth, pinned against gill arches by a torrent of water moving in the wrong direction. Once the mouth closes, the physics shift again. Water is expelled through the gills, but the prey remains trapped, guided backward by specialized structures that prevent escape. Teeth, when present, are small and angled inward, designed not for cutting, but for retention. The prey is swallowed whole or repositioned deeper into the throat, all without visible struggle. The sand settles. The reef returns to its baseline motion. If not for the brief cloud of disturbed sediment, it would be impossible to tell that predation has occurred. This method explains why reefs are full of what can be called vacuum predators. Groupers are not alone in using suction feeding, but they represent one of its most effective expressions. In environments where space is constrained and reaction times are critical, creating a localized collapse of pressure is more reliable than chasing prey through obstacles. Suction does not care how fast prey can swim. It only cares how close it is. The grouper's anatomy is tuned precisely for this role. The skull is robust yet flexible, with bones that can rotate and expand in coordinated sequence. Muscles around the head and throat contract with explosive speed, increasing mouth volume dramatically in a fraction of a second. The hyoid apparatus drops, the jaws flare, and the gill covers swing outward, all synchronized to maximize water inflow. This choreography has been refined over millions of years, turning the act of opening a mouth into a lethal event. The prey's defenses are rendered irrelevant by this approach. Armor does not matter when the body is pulled wholesale into a predator's mouth. Spines and toxins may deter biting predators, but suction bypasses contact altogether. Even venomous fish are vulnerable if they drift too close. The grouper does not need to touch dangerous parts. It needs only to move water. This is why groupers often hunt near the seabed or close to structure. Sand and rubble amplify the effect of suction, making the movement of water visible and more effective. The prey is often pinned against the bottom by the initial inflow, losing what little space it had to react. In some cases, groupers will even angle their strike to use the reef itself as a backstop, ensuring that the prey cannot be pulled sideways out of the suction cone. The ecological consequences of this strategy are profound. Groupers exert strong control over populations of smaller reef fish, shaping community composition through selective removal. Fish that hover too close to the bottom or linger near grouper territories face higher risk, pushing them to alter behavior, feeding times, or habitat use. Over time, this pressure redistributes prey species across the reef, influencing where energy flows and which niches remain viable. Groupers themselves are constrained by their method. Suction feeding requires proximity and precision. It does not work well against prey that stays far from cover or maintains constant motion in open water. This is why groupers are often ambush predators rather than roaming hunters. They choose locations carefully, establishing territories where prey traffic is predictable and escape routes are limited. Ledges, drop-offs, and sand channels become killing zones, not because the grouper patrols them aggressively, but because it waits there patiently. There is an irony to the grouper's apparent calm. To a casual observer, it may look sluggish, even lazy, hovering in place while more active fish zip past. This stillness is deceptive. The grouper is not resting. It is calibrating. Its entire hunting strategy depends on choosing the right moment, not on exerting continuous effort. When the moment arrives, the response is instantaneous and final. This approach also explains why groupers often cooperate with other predators. In some reefs, groupers have been observed signaling to moray eels or octopuses, leading them toward crevices where prey hides. When prey flees the crevice to escape the moray, it often emerges directly into the grouper's suction zone. This cooperation highlights a shared understanding of spatial control. The grouper does not need to enter tight spaces. It needs prey to exit them in panic. From a physiological standpoint, suction feeding places extreme demands on the grouper's musculoskeletal system. Rapid expansion and contraction of the mouth generate significant stress, requiring strong connective tissues and precise neural control. The energy cost of each strike is high, which is why groupers do not strike constantly. They wait until success is likely, conserving energy between attempts. This efficiency allows them to grow large and live long, becoming dominant residents of their chosen territories. The moment of capture is often the only visible violence. There is no prolonged chase, no visible injury, no struggle. The prey is simply removed from the system. This makes suction predators difficult to perceive as dangerous until it is too late. To the prey, danger does not announce itself. It arrives as a sudden absence of water where water should be. As the camera replays the strike in slow motion, the mechanics become clearer. The mouth opens. The water accelerates. The sand lifts. The prey collapses inward, not because it is weak, but because the environment has been weaponized against it. The grouper does not defeat prey through endurance or strength. It deletes the possibility of reaction altogether. After feeding, the grouper resumes its position, fins fanning gently, eyes scanning once more. The reef continues around it, unaware that one of its inhabitants has been erased in a moment too brief to register. Other fish pass by, some keeping a wider berth now, others oblivious. The cycle repeats. This is the defining lesson of suction predators. Survival is not always lost through failure to run or fight. Sometimes it is lost because the opportunity to do either never exists. In a reef where milliseconds decide outcomes, removing reaction time entirely is the ultimate advantage. The grouper does not chase you. It does not poison you. It does not trap you over minutes or hours. It waits until you cross an invisible threshold, then opens its mouth and lets physics finish the job. You do not lose a chase. You lose a moment. The reef shifts character as daylight softens, when contrast becomes more important than color, and motion draws the eye faster than shape. This is the hour when attention is fragile. Shadows lengthen, patterns blur, and the line between background and foreground becomes negotiable. In these conditions, survival belongs not to the fastest swimmer or the strongest jaw, but to the animal that can control what others see, and just as critically, what they fail to notice. From a bed of seagrass and broken coral, the cuttlefish rises, not by moving forward, but by rewriting the scene around it. At rest, the cuttlefish barely exists. Its body hovers just above the substrate, fins rippling gently along the mantle edge like a continuous ribbon, providing lift without effort. The outline is soft, unfinished, its skin textured to mimic sand ripples, algae, or coral rubble, depending on where it pauses. Color matches environment not approximately, but precisely, down to subtle gradients and speckling that mirror light falling across the sea floor. This camouflage is not passive. It is actively maintained, constantly recalibrated as the animal shifts position or as the light changes overhead. The cuttlefish is not hiding behind the reef. It is impersonating it. Beneath this visual deception lies one of the most complex skin control systems in the animal kingdom. The cuttlefish's skin is layered with chromatophores, tiny pigment sacs controlled directly by muscles and nerves, allowing instantaneous expansion or contraction. Beneath them sit iridophores and leucophores, structures that reflect and scatter light, adding brightness, contrast, and structural color. Together, these layers form a dynamic display panel capable of producing patterns, waves, flashes, and false depth in real time. Unlike animals that change color slowly through hormonal shifts, the cuttlefish operates at the speed of thought. Pattern is not a response. It is a decision. The prey does not see the cuttlefish yet. A small fish pecks at the bottom, attention fixed on food particles disturbed by current. It relies on motion detection to warn it of danger, on the sudden lunge or silhouette shift that signals attack. The cuttlefish denies it that cue. Instead of advancing directly, it drifts sideways, adjusting skin texture to break its outline, blending so thoroughly that even trained eyes struggle to isolate it from background. Distance closes without alarm. Then the display begins. The cuttlefish's skin erupts into motion, not random but structured, a traveling wave of dark and light bands that roll across its mantle. This pattern is not camouflage. It is advertisement, but not of the cuttlefish itself. The wave draws the eye away from the head, away from the true source of danger, hijacking the prey's attention with movement that feels important, urgent, impossible to ignore. This is the cuttlefish's light show, and it is not meant to be beautiful. It is meant to be distracting. In neurological terms, the prey's brain is overwhelmed. Sudden contrast changes trigger reflexive orientation responses, pulling attention toward the most dynamic element in the visual field. The prey turns slightly, tracking the moving pattern, attempting to interpret it. Is it a larger animal? A warning signal? A threat approaching from the side? These questions cost time. Time is the only thing the cuttlefish needs. While the prey watches the skin, the weapon deploys. 2 feeding tentacles, hidden until now among the 8 shorter arms, launch forward with explosive speed. They are not swung or thrust in the traditional sense. They are fired. Elastic energy stored in specialized muscle structures releases in a fraction of a second, sending the tentacles shooting outward like living projectiles. At their tips are clubs lined with suction cups, designed not to injure, but to seize and hold. The grab is precise. The clubs strike the prey's body and adhere instantly, suction locking onto scales and skin. There is no chase, no adjustment. The tentacles retract immediately, pulling the prey inward before it can generate thrust or change direction. The entire sequence, from visual distraction to capture, unfolds faster than most prey, can process the fact that an attack has begun. Once the prey reaches the arms, the cuttlefish completes the kill with efficiency rather than drama. Arms wrap around the struggling body, guiding it toward the beak nestled at the center. A quick bite disables, often targeting the head or nerve-rich regions, and the struggle ends. The skin display fades back into camouflage, the reef returning to normal as though nothing unusual has happened. This combination of visual manipulation and mechanical precision is what makes the cuttlefish such a formidable predator in complex environments. It does not rely on brute force or speed over distance. It relies on misdirection. By separating attention from action, it ensures that prey respond to the wrong stimulus at the wrong time. The cuttlefish does not need to be faster than prey. It needs to be earlier. From an evolutionary perspective, this strategy reflects a deep understanding of sensory bias. Most reef fish are tuned to detect predators by movement and contrast changes associated with approach. The cuttlefish exploits this by generating contrast that is deliberately uninformative, a signal without meaning that still demands attention. This is not mimicry of another species. It is interference, jamming the prey's sensory processing long enough for the physical attack to land. The projectile tentacles are equally specialized. Unlike the arms, which are muscular and flexible, the feeding tentacles are built for extension and retraction only. Their structure prioritizes speed and accuracy over strength, relying on the arms to finish the job once the prey is secured. This division of labor reduces energy expenditure and allows the cuttlefish to attempt multiple strikes without exhaustion. If the tentacles miss, they retract instantly, and the cuttlefish can reposition and try again without committing its entire body. This hunting method is particularly effective in environments where prey density is high, but escape routes are complex. Seagrass beds, rubble fields, and reef edges all favor predators that can operate at close range without revealing themselves too early. The cuttlefish's ability to shift seamlessly between invisibility and spectacle allows it to control these spaces with minimal movement. The ecological role of the cuttlefish extends beyond individual predation events. By targeting small fish and crustaceans that graze on algae or prey on invertebrates, cuttlefish influence the balance of reef communities. Their presence alters where prey species feed and how they group, pushing them toward areas with fewer visual distractions or different light conditions. Over time, this pressure shapes the distribution of species across the habitat, reinforcing the importance of sensory environments in ecological organization. Physiologically, the cuttlefish is built to support this strategy at every level. Its nervous system is highly developed, capable of coordinating complex skin patterns while simultaneously tracking prey and timing tentacle deployment. Its eyes are sensitive to polarization of light, allowing it to detect reflective surfaces and subtle changes in orientation that many prey cannot hide. This visual acuity complements the skin display, enabling the cuttlefish to tailor its patterns to the specific weaknesses of its target. There is an understated irony in how this predator appears to observers. The cuttlefish is often described as graceful, intelligent, even playful. Its displays are mesmerizing, its movements fluid and controlled. Yet these same qualities are tools of lethal efficiency. The beauty is functional. The elegance is engineered. What looks like performance is in fact predation optimized for a world where perception determines survival. Even escape behavior reflects this philosophy. When threatened, the cuttlefish may deploy sudden high contrast patterns or ink clouds, again overwhelming the visual field and creating false points of focus. It does not flee blindly. It vanishes behind confusion, leaving predators chasing shadows and afterimages rather than a moving target. The same principles that govern its hunting also govern its defense. Control attention, then move. As the camera lingers on the aftermath of a successful strike, the cuttlefish settles back into the reef, skin smoothing into muted tones, texture flattening to match the substrate. The light show is over. There is no indication that anything out of the ordinary has occurred. Prey numbers are reduced by 1. Energy has changed hands. The system continues. This is the cuttlefish's true power. It does not dominate space through aggression or constant patrol. It dominates moments. Each hunt is a brief interruption in the reef's rhythm, so fast and so clean that it leaves no ripples behind. Other predators announce themselves through movement or noise. The cuttlefish announces itself through spectacle, then strikes where attention is weakest. In a sensory world, controlling perception is controlling reality. The cuttlefish understands this instinctively. It does not need venom, armor, or brute force. It needs timing, light, and precision. You watch the light show, then you are grabbed. The seafloor looks calm at first glance, almost static. A patchwork of sand, shell fragments, and low-growing life anchored to stone. Nothing here moves quickly. Motion is subtle, measured in centimeters and minutes rather than bursts and seconds. To an untrained eye, this environment feels safe, even dull, a place where danger seems unlikely simply because nothing appears capable of delivering it. But this is a misunderstanding born from speed bias. On the seafloor, survival is not dictated by how fast death arrives, but by whether it arrives at all. And few predators demonstrate this more unsettlingly than the starfish. A starfish advances across the substrate with deliberate patience. Hundreds of tube feet extend and retract in coordinated waves, gripping microscopic irregularities in rock and shell. Each foot ends in a suction cup, capable of adhering to surfaces with remarkable strength when multiplied across an entire body. Individually, a tube foot is unimpressive. Together, they form a slow, relentless traction system that never tires, never hesitates, and never abandons contact once established. This is not locomotion built for escape or pursuit. It is built for inevitability. The starfish does not hunt in the traditional sense. It does not stalk prey across distance, does not chase, does not ambush with speed or surprise. Instead, it searches for resistance. A closed shell. A fixed organism. Something that cannot flee once engaged. Bivalves buried in sediment, mussels clinging to rock, oysters sealed tight against intrusion. These animals evolved armor and closure as primary defenses, relying on the assumption that predators would need to force entry violently or pry them apart quickly. Against many attackers this works. Against a starfish, it fails slowly. The first contact looks harmless. The starfish positions itself over a shellfish, arms arching slightly as tube feet explore the surface. There is no immediate struggle. The shellfish senses pressure and responds instinctively, contracting muscles that hold its shells tightly shut. This is its strongest defense. The starfish does not attempt to break this seal through force alone. Instead, it settles in. Tube feet anchor firmly to both halves of the shell. Hundreds of them, distributed across multiple arms, begin applying steady, opposing tension. Not enough to snap the shell open. Not enough to trigger immediate failure. Just enough to exploit fatigue. Shellfish muscles are powerful, but they are living tissue. They require oxygen. They accumulate metabolic waste. They weaken over time when held under constant strain. The starfish understands this without understanding anything at all. Evolution has shaped a predator that wins by outlasting resistance rather than overpowering it. This process can take hours, sometimes longer. The shellfish remains alive the entire time, sealed shut, burning energy to maintain closure. The starfish remains equally committed, tube feet never releasing, pressure never easing. There is no escalation, no dramatic turning point, just persistence versus physiology. Eventually, the shell opens a fraction of a centimeter. That is all the starfish needs. What happens next is one of the most alien feeding behaviors in the animal kingdom. The starfish does not insert teeth. It does not bite. It does not chew. Instead, it everts its stomach. Through the narrow gap it has created, the starfish pushes its stomach outward, turning it inside out like a living glove. This soft, pale organ flows into the shellfish's interior, conforming to the space between the shells, wrapping around still living tissue. Digestive enzymes are released directly onto the prey, breaking down flesh externally. The starfish is not eating yet. It is liquefying. This is external digestion in its purest form. The prey is dissolved outside the starfish's body, reduced to nutrient-rich slurry that can be absorbed gradually. The shellfish does not die instantly. Nerve activity may continue briefly as tissues are chemically dismantled. There is no venom in the traditional sense, but the effect is similar. Enzymes attack cell membranes, proteins unravel, and structural integrity collapses at the molecular level. The starfish does not need to rush. Its meal cannot escape, cannot close again, cannot resist once digestion has begun. From a biological standpoint, this strategy is brutally efficient. The starfish bypasses the need for a large mouth or powerful jaws, allowing it to consume prey larger than its own central body opening. By digesting externally, it avoids ingesting hard shells or indigestible material, absorbing only what it can use. Waste remains outside. Energy efficiency is maximized. Risk is minimized. This feeding method also reshapes the ecosystem in ways that are easy to underestimate. Starfish are keystone predators in many marine environments, capable of controlling populations of shell-forming organisms that would otherwise dominate space. Mussel beds, for example, can overgrow and exclude other species if left unchecked. Starfish predation prevents this, maintaining diversity by selectively removing individuals over time. The horror of the process is irrelevant to the system. What matters is balance. Yet, there is something uniquely disturbing about the starfish's approach because it defies intuitive ideas of predation. There is no clear moment of attack, no visible injury, no blood. Death occurs through gradual biochemical erasure, not trauma. From the prey's perspective, the threat is not a sudden event, but a drawn-out certainty, initiated the moment the starfish's tube feet lock on. Time-lapse footage reveals the true nature of this process. Over hours, the starfish remains motionless, arms spread, stomach extended. The shellfish's tissues fade, collapse and disappear, replaced by empty shell halves and a satiated predator that slowly retracts its stomach back into its body. When the process is complete, the starfish simply moves on, leaving behind shells that look intact, as if nothing violent has occurred. The evidence of predation is subtle, easily missed. This is why the starfish can feel like a mythic creature rather than an animal. Its method resembles something from deep time, a reminder that predation does not have to look like a chase to be lethal. Long before speed and jaws dominated marine ecosystems, there were organisms that fed by waiting, pulling, and dissolving. The starfish is a modern echo of that ancient strategy. Its physiology supports this patience. Starfish do not rely on rapid metabolism or high energy output. Their bodies are decentralized, with nerve rings rather than centralized brains, allowing coordination without urgency. Their tube feet operate hydraulically, driven by water pressure rather than muscle contraction alone. This system is slow but resilient, capable of maintaining force over extended periods without fatigue in the way muscle-based systems would experience it. The starfish does not tire easily because it was never meant to hurry. There is also an irony in the starfish's appearance. Its radial symmetry, bright colors, and gentle movement make it one of the most recognizable and aesthetically pleasing animals on the seafloor. It is often associated with calm tide pools and shallow reefs, admired rather than feared. Yet beneath this familiar shape lies a feeding strategy that is among the most invasive and irreversible in the ocean. Beauty and brutality coexist without contradiction. The prey species have responded evolutionarily, but with limited options. Stronger muscles can delay opening but cannot hold forever. Thicker shells resist prying but increase energy costs and slow growth. Burrowing deeper reduces encounter rates but limits feeding opportunities. No defense fully negates the starfish's approach. It can only be postponed. This makes starfish predation a constant pressure rather than a selective one, shaping populations gradually rather than through sudden crashes. The broader food web absorbs this pressure quietly. Predators that feed on starfish must contend with their tough skin and chemical defenses. Some fish and invertebrates specialize in attacking starfish arms, consuming them piece by piece. Even here the starfish adapts. Its ability to regenerate lost limbs turns injury into inconvenience, allowing it to survive encounters that would be fatal to other animals. Regeneration reinforces its role as a long-term presence, rather than a fleeting one. As the camera lingers on an empty shell, split open just enough to tell the story, the seafloor resumes its slow rhythm. Currents shift sand. Other scavengers arrive to inspect what remains. Life continues around the quiet aftermath. There is no sign of struggle, no dramatic marker of death, only absence. This is the true horror of external digestion. It does not announce itself. It does not escalate visibly. It simply proceeds, step by step, chemistry doing what force does not need to. The starfish never opens its mouth because it does not need to. Its body becomes the digestive system, reaching outward to consume the world directly. On the seafloor, speed is optional. Patience is not. The starfish does not kill you quickly. It does not even look like it is killing you at all. It holds you, opens you just enough, and lets enzymes finish the work while you are still alive. It eats you without opening its mouth. The reef hardens again where light thins and surfaces lose their softness, transitioning from waving coral branches to rock faces armored with calcified life. Here, movement slows not because danger disappears, but because everything has learned to endure contact. In these zones, defense is written directly into the landscape. Spines, shells, plates, and toxins dominate. Among them, the sea urchin stands out not for what it does, but for what it forces others to do. A sea urchin is not subtle. It announces itself as a sphere of danger, a living barricade bristling with spines that radiate outward in every direction. Each spine is sharp, rigid, and capable of inflicting painful puncture wounds on careless predators or wandering limbs. From a distance, an urchin resembles a thicket more than an animal, a patch of the reef that bites back if touched. Fish slow their approach. Hands recoil instinctively. Even currents seem to respect the space around it, bending gently through the forest of spines rather than disturbing it. For a long time in evolutionary history, this was enough. The sea urchin's body is enclosed in a rigid test, a fused skeleton of interlocking plates that provides structural integrity and anchors the spines. Beneath the spines are smaller defensive tools, including pedicellariae, tiny pincer-like appendages capable of gripping, stinging, or delivering venom in some species. Together, these layers create a formidable barrier that deters casual predation. The message is clear. This animal is not worth the trouble. And yet the reef does not reward static solutions forever. Sea urchins feed openly, grazing on algae and encrusting organisms, shaping reef structure in the process. In moderation, this grazing prevents algae from smothering corals, maintaining balance. In excess, it strips reefs bare, transforming vibrant habitats into barren rock. This influence makes sea urchins ecologically powerful, and ecological power attracts attention. Predators evolve not just to eat, but to control. The first wave of attackers approached with force. Fish with crushing jaws learn to bite through spines rather than around them. Triggerfish, for example, circled patiently, flipping urchins over to expose the softer underside, attacking from angles the spines were never meant to cover. This behavior is not instinctive at birth. It is learned, refined, through repeated encounters and observation. Younger fish hesitate. Experienced ones do not. Broken spines litter the seafloor around feeding sites, evidence of trials that ended poorly for the urchin. Other predators bring different tools. Some wrasses and pufferfish use suction feeding to remove spines one by one, clearing a path to the test beneath. The process is deliberate and careful, minimizing injury while dismantling defenses piece by piece. What looks like armor becomes a series of removable obstacles. The spines still hurt, still puncture, but pain alone does not stop an animal that understands the reward. Then there are predators that bypass spines entirely. Octopuses descend like shadows, arms exploring between spines with impossible flexibility. They do not need to break the defense. They need to ignore it. Suckers grip the test itself, anchoring between spines, applying leverage that spines cannot counter. Once secured, the octopus uses its beak to drill through the test, injecting venom that paralyzes the urchin internally. The spines remain intact. The defense works perfectly against teeth and claws. It simply does not matter. Moray eels approach differently, using the reef structure to their advantage. They wedge urchins against rock, applying pressure until spines snap or bend, then seize exposed sections. Even sea turtles join the escalation, using powerful jaws to crush entire tests, spines and all, turning a defensive forest into calcium debris in seconds. Each predator represents a different solution to the same problem, a testament to how pressure reshapes behavior over generations. The sea urchin responds as it always has, by reinforcing the same strategy. Thicker spines, longer spines, more venom. Some species develop spines so fine and brittle that they break off in wounds, increasing irritation and infection risk. Others incorporate toxins that intensify pain or disrupt muscle function. These adaptations are not useless. They still deter inexperienced predators. They still reduce encounter rates. But they no longer guarantee safety. This is the core of the arms race. Defense does not end predation. It filters it. As spines become more dangerous, only predators capable of handling them persist. Those predators gain access to a food source others cannot exploit, reducing competition and reinforcing their specialization. Over time, this dynamic selects for attackers that are not just stronger, but smarter, more patient, more precise. The reef becomes populated not by generalists, but by experts. From an ecological perspective, this escalation has cascading effects. When predators effectively control sea urchin populations, reefs flourish. Algae remains in check. Corals regain space. Biodiversity increases. When predators are removed, often by human activity, urchins explode in number, grazing relentlessly and converting complex reefs into flattened landscapes. In these moments, the sea urchin's defense is irrelevant. Its success depends not on invulnerability, but on the presence of enemies capable of killing it. This inversion reveals a deeper truth. Defenses are not designed to make an animal untouchable. They are designed to make it expensive to eat. The sea urchin's spines raise the cost of predation, but cost alone does not eliminate demand. It simply shifts who is willing to pay. The chemical dimension of this arms race adds another layer. Venomous spines introduce physiological consequences that extend beyond immediate injury. Predators that survive encounters may experience lingering pain, infection, or reduced feeding efficiency. These sublethal effects shape behavior, teaching predators how to handle urchins more carefully or avoid them under certain conditions. Learning becomes as important as strength. The reef remembers through behavior. Sea urchins themselves exhibit limited behavioral flexibility. They cannot flee. They cannot hide quickly. Their survival strategy is entirely structural and chemical. This rigidity makes them reliable targets in evolutionary terms. Predators can specialize around them because their response is predictable. The spines will always be there. The test will always be rigid. The urchin will always resist in the same way. That predictability is both strength and weakness. As the camera drifts across an urchin field, the seafloor looks hostile, bristling with hazards. Fish navigate carefully, maintaining distance. But look closer, and the signs of breach are everywhere. Spines snapped cleanly at the base. Empty tests split open. Predators circling, assessing, waiting for the right angle. The defense works, but not universally. Not permanently. In this environment, escalation never stops. Each improvement in defense is met with an innovation in offense. Each new weapon selects for a new countermeasure. The reef becomes an archive of solved problems where no strategy remains dominant for long. There is a quiet irony here. The more dangerous the sea urchin becomes, the more it incentivizes the evolution of predators capable of extreme solutions. Crushing jaws, tool use, chemical drilling, precision manipulation. The spines do not end the conflict. They refine it. This pattern repeats across the reef. Lionfish venom selects for predators with immunity or novel hunting tactics. Shell armor selects for suction and leverage. Camouflage selects for pattern recognition. Every defense sharpens the ecosystem, pushing it toward greater specialization and complexity. The sea urchin stands at the center of this dynamic, unchanged in appearance, ancient in design, yet constantly shaping and reshaping the behaviors around it. It does not chase, strike, or poison aggressively. It simply exists as a problem to be solved. And the reef solves it. As twilight deepens, predators resume their patrols. A triggerfish tests an urchin's balance. An octopus explores the spines with careful arms. Somewhere, a turtle approaches with indifference, jaws capable of ending the encounter outright. The spines remain sharp. The defense remains real, but it is no longer decisive. This is the final lesson of the arms race. Protection does not eliminate danger. it transforms it. Every wall invites a battering ram. Every toxin invites resistance. Every spike invites a strategy. The sea urchin survives not because it cannot be eaten, but because it cannot be eaten easily. That difference is everything. Defense does not stop the reef. It just selects for nastier attackers.